Yeah, hi. Good evening, everyone. Welcome to the Week 2 open session. Uh, am I audible?
Yes, sir, you are audible.
Yes,
Good
sir.
one. Good evening.
Yes, sir.
Thanks for confirmation. Yeah, so today is the Week 2 open session, and I hope you have already watched the videos, lectures of the professor. Uh,
Yes, sir.
Before starting, if you have any doubt in the topics of the Week 2, so first
Sir,
I'll take your query, then if no query, then I will discuss the thing. Okay.
sir, I have a doubt.
Yes, yeah, they was.
Sir, I have a doubt in the merge sort function. I was able to understand the merge function itself,
Mhm.
but then sir introduced the recursive merge sort that was sorting the function. I wasn't able to understand that part. How is it returning sorted list?
Okay, so you are not able to imaginate that recursive part.
Yeah,
You're saying.
I was able to understand the concept what it was saying, but I wasn't able to imagine the recursive part what it is returning, because in my mind it was returning only the last element separately, not combined in a list.
Okay, okay, sure. So then definitely we will discuss this. Any other doubt?
And one is in PPA1. It is
PPA one.
although although I wrote the code of the binary search and all, but
Mm-hmm.
I am getting error not able to run.
Okay, okay, sure. We will
Sometimes
discuss
it
that.
run and sometimes it
Uh,
says not able to run.
Sir, apologies to the interrupt here. So this
Mm-hmm.
is the open session.
Yes.
So are you going to discuss about the topic the students are getting issues, or like you're going to take the topic completely from yourself and
Yeah.
cover
So
all the topics again?
open session means basically I will discuss your doubt. If there is no doubt, then I'll discuss the topics.
Sir, can you take the top doubts at the end of session, sir?
End of
Uh,
the session. Yeah, so
yeah.
because of that I am asking the query first. So if that query is covered in the that summary part in my summary,
Sir,
so definitely we will
yes,
discuss.
sir, because somebody asking the PPA questions, and we haven't gone through the PPA as of now. So it feel like, adding difficulty.
Okay.
You understand, right? So my request is just come. I mean, take your session theory, the theory, whatever session as according to your plan.
Mhm.
Then you take the student questions, sir.
Okay,
At
okay.
Yes,
least
sir.
Most,
Agreed.
yeah,
relate
most
actually.
most of the time we just summarize the all topics of the week.
Yeah.
Okay, because many of students are not asked the doubt in this open session, so we discuss all the topics and other things. We are also starting TA session from this week. So that TA session we will conduct on this Monday 5 to 7 and Tuesday 5 to 7 and Thursday 5 to 7 in evening. Okay, so that session actually ta will take, and that session is specific for your this practice assignment. You can ask anything in that session, and that session will not be recorded. So if you have any specific problem in the programming assignment, and if deadline is over, then you can also ask the graded programming assignment and graded assignment questions. So if you have any doubt, you can join that session and you clear your query. Okay.
Sir, sir, I haven't get the TA session schedule in my calendar. Is it?
I think check again. So that is now visible. We have already scheduled in the calendar. So if you are able to see this session, now can check the tomorrow date. You can see the TA session also. Otherwise, we have sent one announcement on the portal. You can see the inbox part of the portal, or we have also posted on the discourse. The
Sir, it
schedule
is visible in the calendar for
calendar, no?
tomorrow.
Yes,
Sir,
Yes.
for
the
tomorrow.
timing of TA session is matching with DBMS and Java sessions also.
Sir,
What?
sir, it's matching in DBMS and SC also.
Yes, to
Okay.
what to
Actually, what happened, that session is actually running in the highest quantity. So we cannot remove every classing. So this session is basically for your clear your doubt. If you have any doubt, okay, so you can join either Monday or Tuesday or Thursday. Okay, but no need to join every session if you have no doubt.
So, and sir,
Okay, so
why this session is happening then?
this session,
Current session, why this is happening?
this is our instructor session. Actually, this Wednesday and that Friday is instructor session, and other three sessions are TA session.
So that I got it. So what is the agenda for today's
Yeah, agenda of today's session is open session where we can discuss your doubt, any doubt, and also if there is no doubt, then we will summarize the week content. Okay. And that Friday session is the coding session, so live coding session. So in that session we release new problems in the Replit team. During the session you have to solve these problems.
So when are the doubt clearing sessions?
Yeah, so today is the doubt clearing session, but
Oh,
in TA session you can join in any session and you can discuss your
when are
doubt.
the TA sessions?
Yeah, Monday, Tuesday, and Thursday, 5 to 7 p.m.
Okay, thank you, sir.
Okay, you can check your calendar also, so that calendar event will be visible to you.
It is not written in the calendar. That is why I asked.
No, this is scheduled from tomorrow. So if you check
Okay, okay,
tomorrow, so you will find that.
okay, okay.
Okay. So, but
Okay,
that session will not be live streamed or recorded. Okay. So if you have any doubt,
okay,
join the session and ask your query. Okay.
okay. Thank you, sir.
Yeah. Siva Bhaskaran.
Hello, Professor. Got a quick question. In the GRPA, right, one of the private test cases is not passing. So, is there a way to get the private test cases?
You are saying that only one private test case is passing of GRPA?
In GRPA 2, okay. I tried the linear search, but linear search is not allowed, right? Because it is some timing consideration, that's why it failed. Okay,
Okay.
find the maximum. But so I tried doing the what do you call it? Logarithmic search, binary
Yes.
search.
Okay.
Okay, in the binary search, right, all the public test cases are passing. Okay,
Mhm.
however, when I try submitting using the private test cases, both the test cases are failing.
Okay. So actually, for in the assignments, if uh, efficient solution is asking, so maybe that public test case are small test case, so that small test case cannot be verified for the time complexity. But in private, actually, long test case are configured. So that test case only be passed if you are writing the that login solution, that
I
efficient
have written
solution.
I have given the login solution only.
So, but I'm not sure. I have to check your code first, then I can just say that your code is login or not. Because
Okay.
because if you are using slicing, so I found that many students use list
I did
slicing.
not use slicing. I did not use slicing.
Okay.
Okay.
Okay, so then just check the corner things, corner case things. Just figure out that what type of inputs are possible for the problem. So just read the problem statement carefully and just figure out that what type of inputs are possible.
Okay.
Okay, so maybe some corner case are not covered by your solution.
Okay.
Okay, because of that, some test cases fail.
Okay. Because I know it is a login solution. I calculated the runtime of it. Okay.
Okay, okay. So, but still in Python, actually, that some direct operation is also takes some additional time. So that, for example, this slicing I have discussed, this in operation is also takes order of n times. But
No, I did not use in. It's basically I had 2 pointers left and right.
okay,
And if the see, I'm just giving the broader algorithm. I'm
okay,
not
okay,
reading
fine.
the code. Okay.
Then if
So
then check the corner case, what inputs are possible.
okay.
Okay, and just figure out it. Hmm. Okay. Yeah, Amitav.
Yeah, sir. I am actually facing to understand the complexity of the code. Oh, so for simple thing, I am quite. It is not a problem. But when there is a lot of evils and other things are coming,
Mhm.
then I am really struggling. So can you help me with some
Yeah, so
example?
that we will start from this topic today. Okay. So yeah, okay. Satyam Jha.
Sir, you said that on Friday we have the live coding
Hmm.
session. So this Friday, what will we do? We do from start from week 2,
No,
like
this
week 2
yeah,
live
this
session.
Friday yeah, week 2. So some new problems will be released on the Friday based on the week 2 content. Okay, so maybe that problems
Okay, sir.
will help
And you,
you to solve the graded problem also. So how you can just solve the graded problem.
And like in this session we will solve the all the problems of the life together, right?
Yes, sir. So you have to just try to finish all the problems during the session, because our aim is to,
Oh, oh,
for this session is to just practice for the OPP exam. Okay, so where you have to
okay, okay,
complete the 4 problems in 2 hours. So just practice in the similar way.
okay, sir. Okay, thank you.
Okay, yeah. Okay, so then I'll start from the first topic, this complexity things in the big two. Let me share my screen. Okay, I hope my screen is visible to all. Okay. So first thing, so this week two, the main contents are actually this complexity things, how we calculate this complexity, and after that the searching and sorting algorithms. So 3 sorting algorithms we are learning in this week, but one remaining quick sort we will also learn in the week 3. That is also sorting algorithm. So we will start from the complexity things. Okay, so what is complexity and why it is required for this algorithms and our solution. So basically what complexity is represent, and what type of complexity we generally measure, and what which complexity is more important. So complexity of an algorithm is a function. So basically this is a function which describes the efficiency of the code efficiency, and we just figure out some measures or some parameters to check this efficiency of the algorithm. So suppose if we are writing the solution or algorithms for any problem. Okay, so there are more than one logic, or more than one different types of solution logic is possible for one problem, same problem. Okay, so at the time, which algorithms is good, which logic is good, which solution is good, how we can compare the solutions or algorithms. Okay, so to compare the algorithms, we generally use 2 types of measures. This first is space complexity, and second is time complexity. So according to the name, if you can simply identify that what is the meaning of space complexity and what is the meaning of time complexity. So space complexity means if you are writing any algorithms. Okay, so or algorithms, or then you are writing some solution code or implementation. Okay, so what size is it, your solution code is taking. Okay, so there are 2 types of size actually we consider for that. One is fixed part. Okay, fixed part is size of code. So what your implementation, what that file, what size is that file is actually taking. Okay, so that is fixed code. If you have written one code, that will be the fixed set of lines or set of instructions, so that will take a fixed amount of memory. But another is another sizes depend on your input variables. Okay, what data structure or what data types you are using. So another that space will depends on this input type. So suppose if you are writing a sorting algorithms. Okay, so sorting algorithm you are writing. So where if input is if you are giving the input for 10 element list. Okay, so if you are giving a list which have only 10 elements, so that means your data structure is only storing 10 elements. So size will also be depends on this 10 elements. Basically if one element is taking 4 byte, so that means 10 element will take 40 byte. So but your algorithm should also be able to sort if you are giving the more input, large input, like if you are giving like 1,000 elements in the list. So that will also be sorted by your algorithms, but at that time the data structure will take more memory. So that actually a dynamic memory required. Okay, which is depends on the input size, what input size you are giving to the algorithms. So that is a variable part. Okay, so that variable part depend on the input size and decided on the input. Okay, so if we combine this both constant part and this variable part, so we can say that this is the total space required by the algorithms. Okay, and what is time complexity? Time complexity means how much what amount of computer times it need to run the application or run your program or run your that algorithms. Okay, so computer times is not a clock time here. Okay, uh, basically, if we just relate to this in the normal clock time, so that is also related to the computer time. Basically, if suppose if you have written some solution code where your that code contains 100 sequentially 100 instructions, okay, which is performed one by one. Each instruction taken one unit of time. So I'm not giving any quantity in second, but I'm just considering that 1 unit of time. If one instruction is taking 1 unit of time, and you have 100 sequentially instruction in your solution code, so that means 100 unit of time is required by your solution code when it is running. And similarly, another solution we have which only have 10 instruction to execute, okay, so that will take 10 unit of time, and that unit of time is directly related to the clock times also, okay. So but this clock time is depends on the processor speed or the configuration of the systems. So we generally not use the terms this clock time here for to the calculate the time complexity. So but we just calculate the number of instructions which are executing at the running time. So how many instructions are executing at the running time, we just try to count that number of instruction to just represent the time complexity, and we consider it a 1 unit time for one instruction that is executing. And this is a theoretical calculation for the time complexity. This is not a exact, okay, but this is more closer, is this which represent how many instruction are executing in the terms of input size, what input size we are giving to the problem, and based on that input size, in the terms of input size, how much instruction are executing by our algorithms. So that things actually we are trying to calculate in the time complexity, okay. So time complexity is the number of instructions which are executing during the running time of the algorithms or that solution code. So that we will just figure out that how the relation is actually occurred in input and number of instruction by the algorithms. So that relation actually we will just figure out that. So next thing is time complexity calculated in 3 types of case. So based on the problem scenario and input types, we can just figure out that what type of case we are calculating the complexity. So suppose same algorithms can take a smaller time amount of time for some specific type of input, okay, and that time is actually very minimal time by the algorithms. So for example for this is suppose if you are searching a element in the list that contain the random elements, not the sorted element, okay. uh, okay, so but what happen if you're searching a element and that element is only located at the first position. So at that time your searching algorithm will take only one steps, and so after one comparison you will find that yeah, element is exist in your list. Then better how many elements are exist in your list. So at that time we can say that only one comparison is required to find out the elements in the list. And so this is actually, we can say that this is a best case, okay. Best case, that means where we are finding the solution in minimum time. Opposite is worst case, if you are searching any elements and that element is located at the last position in the list, but if you are trying to comparison each element from the starting one by one, okay, at that time you have to compare all the elements for the searching with the searching element one by one, and after all comparison, in the last element you will find out that yeah, element is exist at the last position. So at the time you have to compare all the elements with the list. So if suppose if your list contains n element, so that means n comparison is required to find out the solution. So that is the maximum time, okay. And so that is represented at worst case, when your algorithm is taking the maximum time. In such a case, when your algorithm is taking maximum time, that is called as a worst case situation. Average case is just a average of all possibility, okay. Suppose if you are searching any element from the list, so that may be located at first position, second position, third positions. So if you calculate the average of all possible solution, that is considered as a average case. Okay, so these three cases generally we used for to calculate the time complexity, but most of the time we just try to calculate the worst case situation only. Okay, because our main goal is to reduce this worst case situation where our algorithm is taking maximum time, and we want to just reduce this worst case time complexity. Okay, and most of the time we will calculate only this worst case complexity for most of the algorithms, but initially in sorting algorithms, or maybe we will discuss all three cases. So now what is, how we can calculate and how we can represent the this count number of operations for any algorithms or code. So growth rate of function, the 1 second. Yeah, Karthikeyan.
This best, worst, and average is only for
Mhm.
time, not for space.
So we can also use for space also, but that is depends on directly input then. Okay, if you are giving very small input size, that is actually best case. Otherwise, I think this is not depends on the for the space. Okay, because if you're what is the input list size you are giving to, and so what variable you are taking during the implementation, so how much space actually you are using at the running times, so that space actually we are calculating. But generally we not use this best case, average case, and worst case for the space complexity.
Thank you.
And also this in the time complexity and space complexity, so this time complexity is more important because sometimes space is also important, but there is one trade-off is also there in this time complexity and space complexity. So for some algorithms, if we increase the space, then in that case we can reduce the time complexity. If we want to reduce the space, then the time complexity will be increased. Okay, so this is a we generally called as a trade-off. uh, so we just figure out that what we need to should reduce. So basically time complexity is more important, and we will discuss time complexity things during this course. We are not covering this space complexity calculation of these things, because time complexity is more important for the algorithm comparison. Our algorithm should be fast. Okay, so yeah, next thing. So growth rate of function. Yeah, so here one example is given. So this example I have written just only to just add the n first n numbers. We can see that or 1 n times, not 10 times. Okay, so just random code is given. Okay, and here we are just starting initializing s equal to 0 first. So this is one instruction. Second instruction is a for loop. That loop is running from 0 to n minus 1. Okay, and nested loop we are using for j. So that loop is also running from 0 to n minus 1. And after that, inside the nested loop, we are just performing one instruction s equal to s plus 1. We are incrementing this s by 1. And finally, we are printing the value of s. So function is just represent the total number of instruction which are executing during the running time in terms of n. Okay, here we are taking this n as a input, so we can just pass any value of n and then we can get the solution. So here we can consider that this n is our input here. Okay, so what n we are giving, so that is our input, and we can just pass any value for this n. And so we will just calculate our function in this in the term of input size n. So here so you can see this is a single operation. Okay, as just imagination that this program is running. So how many times line number 1 will be execute? So are this first instruction is dependent
Once.
on the input n. So this we are considering that this is an input. Okay, so only line number 1 will only execute one time in the program, correct? So this is not dependent on the input, and this is a single instruction and will only execute only one time. So we are just writing this is taking only 1 unit time. Only one time this instruction will execute. After that, second instruction. Okay, so in this this is a range. So this is a for loop, and this for loop is running from 0 to n minus 1. Okay, so this is the range. You know that range start from 0 and it just run till n minus 1, and after that this is the termination condition. Okay, when this I value is reached at the n, that will be the termination condition. So internally actually this loop is runs like that. So I is start equal to 0, and it there is one conditional statement is so this is n minus 1, and every time what we are doing, we are incrementing I plus plus. Okay, so this is the initialization where we are starting this loop. This is the condition. So every time we will increment our I by 1. So this is increment operation, and we will check this condition. Every time we will check this condition. If our this condition is satisfied, then we will enter inside the loop. Okay, so what happened? This condition will be satisfied for 0, 1, 2, 3, dot, 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 n minus 1. Okay, so how many steps we will find out this? This is n steps. Okay, we are starting from 0, and this is the last step. And one step where this condition will not be met, and that loop will terminate. Okay, so when the I become n, so at that time this condition will not be satisfied, and at that time this loop will terminate. So one condition is for terminate condition. Okay, so this line number 2 will execute n plus time, one time. Okay, and this is not if we are just calculating the fixed things. You can also ignore some single step, two steps. So because we are calculating this complexity theoretically. Okay, so this is not a exact number.
No, sir, I don't get it, sir. How it is n plus 1?
Yeah, so this loop, how many times you will enter inside this loop?
So if it is a 0 to 5, okay, so I enter 5 times.
5 times, but
N times.
one more time this loop will check, and that at that time this loop will, that condition will not be satisfied.
Okay.
Okay, that is a termination condition. This is this loop is similar to this while condition. Okay, so we are, if I write this I equal to 0, and if I use while when I is less than equal to this n minus 1, and inside this while loop I just incrementing by I equal to I plus 1. So this is equivalent. Okay, this for loop is equivalent this while loop. We are starting from I equal to 0, we are checking the condition, and we are entering inside. If this condition is true, we are entering inside the while loop. Then inside the loop, we are after performing all the operation, we are incrementing our I, and then again checking the condition. Okay, so at that time, if our n value equal to 100, so this condition will be satisfied 100 times. Okay, but one more time, last time, when this this I will become 100, this equal to 100. Okay, so 0, this 100, 0 to 99, but when I become 100 after incrementing, so this condition will not be satisfied. At that time this loop will terminate. Okay, so but still this instruction is executing, okay, to check the condition. So because of that, n plus 1 we are taking. So how many times this loop will execute actually n plus 1 time. Okay, so this is n plus 1. Now the nested loop. Okay, so just check this line number 2. How many times this condition will be satisfied, and how many times you will enter inside the loop? N times.
Yes,
sir.
Okay, so you are entering n time inside the loop, and this so for every time. Okay, so for every value of I, suppose I equal to 0, now inside this part will execute. Okay, so for every value of I, this j loop will run this end this time. Okay, so for I equal to 0, this j will similar for so just consider as the previous loop. So here we are taking I equal to n. Now this j will also start from 0 to n minus 1. Okay, so this is total n, and one condition for termination condition. Okay, termination. So this is n plus 1. Okay, so for every value of I, this j loop, this line number 3 will also be execute n equal n into n plus 1 time. So for every value of I. Correct? Okay, then so for every value I equal to 0, this j is running n times. Okay, and how many times this second loop you will enter inside the second loop? N times. Okay, So similarly, I equal to 1, this j will run n times. I equal to 2, this will run j equal to run n times. So similar way, when I equal to n minus 1, so this is j will run n times. Okay, so total n into n, we can say that. Okay, so n into n, this statement will execute n square time.
Sir, the J loop will run for n plus 1 times. Every time it will have to check whether J has become n plus 1.
No,
The
yeah.
value
So
has become n
this
plus 1.
line number three will
3,
execute this
it will
n
be
into
n
n plus 1.
into n plus 1.
Correct. But how many? So only you will only enter n times inside for every j loop.
N times, that is why we have this multiplication of n into n plus 1.
Yes. No, this is for, so this also contains the terminate condition. Okay,
That terminator
this
is
one.
n plus 1,
Huh.
plus 1.
Yeah, but you will only enter inside this j loop only n times for every value of I.
That is right. That is right.
Huh.
Because the moment I becomes n plus 1 the last time, it will encounter I is not less than n minus 1. So it will come out of that. So it
Hmm.
will not enter the J loop at that
Yes.
time.
Okay. So how many times this line number 4 will execute according to you?
N into n plus 1 times.
No, why n plus 1?
No,
N squared.
n into n square times.
So
N
total
square times.
n square time, correct? Na?
S is equal to s plus 1 will be n square times.
Yeah, this
Because
first,
the moment it is the plus 1 time, it will come out.
yes, correct. So this line number 4 will only execute n square times, correct? And this line number is n into n plus 1, and this is n times, and this is 1 time. And how many times this last print statement will execute? Only one time?
For I loop will be executed n plus 1 times.
Yeah, n plus 1, sorry. Okay. Okay, so line number 5, how many times this will execute?
1.
One times in the loop. Okay, that when this is running. Okay, so one time. So if you combine, if
Sir,
you
I didn't understood fourth step.
step number 4.
Yes,
Okay.
sir. How come it's n square?
Okay, 1 second. So how many times you are entering inside this loop? N times. Okay, so I equal to 0, I equal to 1, I equal to 2, and this I equal to n minus 1. So these are the steps when you will enter inside the nested loop, correct?
Yes, sir.
Okay, so these value are actually n values, 0 to n minus 1. If you count this is n. For every value of I, this j loop will run n plus 1 time. Okay, so this 0 to n minus 1, for where this condition will be true, or you will enter inside the second nested loop. Okay, so inside the j loop, but one more time for the termination condition. So because of that, this is n and this is plus 1. So for each value of I, j is running n plus 1 time. Okay, so we are entering inside the I loop n times. Okay, so total number of times this j loop will run n into n plus 1. So this is clear?
Yes, sir.
Okay, but how many times for every j loop, how many times you are entering inside the j loop? N times this.
Yes, sir.
Okay, this is n times you are enter inside the uh, j loop. So this instruction will execute. So this instruction is executing n times for every value of when you are entering for this j loop. So when I equal to 0, j is, you will enter n times for this statement. You will execute this fourth line. Okay, and similarly I equal to 1, n times. So I equal to 2, n times. So similarly, you have n value of I, then n into n, total n square.
Yes, sir. Understood now. Thank you, sir.
Okay, so if you add all these steps, so if you add this 1 plus n plus 1 and n, this will become n square plus n. Okay, after multiplying this inside this, So this will become like this, and this is n square and this. So if we add all these steps, you will get this type of function. Okay. Okay. So after adding this, so you will get this function fn equal to 2n square plus 2n plus 3. So if you add all these number of steps, you will get this. This is function. This is the function fn equal to 2n square plus 2n plus 1. This is directly representing the relation between input size and total number of steps, this function. But to represent the complexity, to represent the complexity of this function, we always choose the highest order of n, that is represent the highest relativity in the terms of input. Okay, so we have three terms here, 2n square, 2n and 3. So this is a constant term. Okay, so this is a fixed term. And similar, this 2n, this is also not dependent, not representing the higher relativity of the input side, but this is the highest order of n, which directly related to the relation. So suppose if your input is n equal to 10, so we can directly relate that n square. So this is the highest order. So that means 100 instructions are required to execute by this function if we are giving n equal to 10. Okay, so a smaller part, to represent the complexity, we ignore the smaller terms or constant part from our function. Okay, and so we will just ignore this 3 constant, 2n constant, also this this part also. Okay, 2n, this is also a one constant part, and we will only use the highest order of n to represent the complexity. So this is the n square. So here we can see that this fn is proportional to n square. If we are giving any value of n, our total number of instructions will execute n square. So this is representing the time complexity of the given code. Okay, so this is the simple idea of what we are trying to calculate if any code is given, any algorithm is given. But the next thing is, okay, so here I am just representing n square, simple direct number of steps based on the input size n. But we can also represent with the help of notations. So here the notations is actually curves. We generally not directly related this relation as a n square. We use some notations to represent the complexity. So that notations is actually, we have three type of notations. One is big O upper bound. Okay, so yeah, yes, wait, sorry.
Sir, like if we have two function, 2n square plus 2 and 3n square plus 3. Sir, then 2n square plus 2 will be better function, I think. So how we can compare it with time complexity?
So first thing, are you able to just figure out that what we are trying to solve here? You have two functions. You are saying that you have two different function here.
Yes, sir.
Okay, so from each function you have to calculate the complexity.
Yes, sir.
So suppose you are saying that so you are saying that fn equal to one function is given like 2n square plus 3, and another function is fn equal to what?
3n square plus 3.
3n square plus 3. So here also, what is the complexity is actually for this? This is we will only use n square. Okay. Yes. So this is also a n square. So here both are the same complexity algorithms. Both are same. We will consider as a similar time algorithm.
Sir, but means fn 2n square plus 3 is better, na, sir?
Yeah, this is better, but this will take some amount of time less compared to the another algorithm. But generally, to represent the complexity, we only use the highest order of relations in the terms of input. So according to that,
means minor thing.
Minor things we ignored actually.
Yeah, so just actually what is happening, so if you take a small number, it doesn't get the difference. But if you take a 1 billion, then square terms dominate. Others, nothing is dominating. So that is just, I think, sir, is trying.
Yes. So generally, because of that, I'm saying that worst case we are just trying to figure out that, and also we calculate this times for the large input.
Yes, sir,
Small
got it.
small amount of input we cannot figure out the much difference, but for large amount of input you can figure out. Okay,
Okay.
so because of that we only just use the highest order of n, which is actually directly related to the much difference. Actually this is representing the much difference actually. Okay, so
Okay.
if two algorithms you have n square and n3, then for large input the difference is very large.
Sir,
For the
but
difference.
if we take very large n, like
Hmm.
1,000 or 1 lakh, sir, then the difference will be more in both the function, I think.
Yeah, difference is there, but that is like similar to 2 into suppose you are giving 10 to the power 5 and another is 3 into 10 to the power 5.
Yes, sir.
Okay,
Yes.
but for the computer system this is not much difference.
Okay, sir, got it.
Okay, this constant term is not a much difference, but
Thank you.
if you are writing like 10 to the power 5 and 10 to the power 7, so this is the much difference.
And sir, these constant term are different for different computer, like some processing power is high of some computer.
Yes, because of that we are not considering this clock time.
Yes, sir.
Okay, we are just using one standard things, and we are trying to count the number of instruction, because number of instruction, this concept standard is actually same for the each algorithms, but if we calculate the times of the computer we cannot compare the algorithm if algorithms are running on two different computer.
Okay, sir, got it. Thank you, sir.
Okay, so because of that we are just trying to figure out some standard comparison parameters so that we can calculate for algorithms, and that will be verified for each system. Okay, so yes, yeah. So next thing is notation. So notation, we generally use three types of notation. So big O notation, omega notation, and theta notation. So big O is generally called upper bound, and omega called lower bound, and theta called as a tightly bound. And when we use this big O notation, when we use this omega notation, and when we use this theta notation, so some conditions are required to satisfy it. So after calculating the function, okay, so suppose if we have one function like this, so this fn equal to 2n square plus 2n plus 3. Okay, so I am writing this function here. So fn equal to 2n square plus 2n plus 3. Okay, so now according to the big O notation is this middle one. Okay, here condition is that we can write this fn equal to big O gn. Okay, so gn, this is a new function we will calculate by the given function. So this is the given function equivalent to fn. So what is the actual time of this fn? We will calculate one gn function, and with some constant. So the cgn is one constant. If we satisfied one condition, if this fn is smaller than or equal to cgn. Okay, so we will figure out the another function gn with the in the terms of highest order of n, this n squared terms. Okay, and if the value of c, this cgn, this part is always greater or equal to the actual fn, this fn is the actual function, complete function. Okay, if we can figure out the new functions, this gn, and with some constant, the value of that this new function cgn will always be greater than or equal to the actual function fn. So if we can prove this condition, then we can write our complexity like fn equal to big O gn. Okay, now how we can prove this? So suppose a function is given fn equal to 2n square plus 2n plus 3. So I'm now 1 second. So I'm opening the tab. Here. So I'm writing fn equal to 2n square plus 2n plus like 3. Okay, so and I want to calculate the function gn. Okay, so what we can do? So suppose this 2n square. Okay, 2 sorry 2n square plus 2n plus 3. I can say that this is equivalent to 2n square plus 2n plus n if I take n is equal to 3. Can I write this? N or not equal to, greater than equal to 3.
Correct. Yes, yes, yes.
Okay, because at this place, okay, I just only changed 3, I just replaced by n, and I'm taking the value of n is greater than or equal to 3. If I'm taking this 3 equal to 3, then both sides will become equivalent. Okay, if I'm taking n is 4, then the right side function is greater than the left side function. Correct? So for this condition, for if I'm taking this n is greater than equal to 3, so this condition is 2. So I'm writing this condition is like this, plus 2n plus 3 is less than equal to 2n square plus 3n. Okay, this is correct for this condition. Okay, now I want to just remove this, convert this to 3n into the terms of this n square. So can I write this n square is greater than equal to 3n? Okay, if I take this condition, n square is greater than equal to 3n, then I can replace this 2n square plus 2n plus 3. Now this is equivalent to 2n square plus 3n, and this is now next condition I'm trying to write here is 2n square plus n square. I just replace this term by this n square, and then I'm taking this condition n square is greater than equal to 3n.
So here n is greater than should be 1, na?
Sorry?
In the last condition, n should be greater than 1.
No, I'm not. I'm taking this condition. N square is greater than equal to 3n.
No. So if the n is equal to 1, then 1 is not greater than equal to 3.
But sir has already satisfied that n is greater than equal to 3 in the very first.
Okay, got it.
Okay, so this condition I'm writing here, this is satisfied or not? If I replace this n square by 3n, then both become equivalent. Correct? If I'm taking any value of n square which is greater than 3n, then this part will become greater than to the previous part, 2n square plus 3n. Okay.
So, sir, I have a question. My question is that, so in the first step, 2n square plus 2n plus 3n, 2n plus n, you take it like this. So in the first things, if I say that 2n plus 3 is greater than less than n square, in the first two terms, if I take like that,
what you are trying to replace?
I am trying to replace at the first last two terms, 2n plus 3. I want to replace with the n square. Can I do the?
So you can do. So actually, what we are trying to just prove it. Okay. So you can also write like n square is greater than equal to 2n plus n, like this. Replace this term directly. Okay. Then you can figure out that. So we are just figuring out one new. We are calculating the gn function in the terms of a highest order of n, and that will always be greater than equal to the actual fn. We are just calculating this gn. So you can just prove in the different way also. This is not a fixed way. So you can take any assumption in between. You can take any value for n and replace by this, and figure out that what is the highest term which is always greater than or equal to the actual fn.
So my first condition is that n should be greater than 3, and from there you start the proof. You are not changing the value in between. Sir, so what I want to say that when you say 2n plus n, in this first step, 2n plus n, okay? So here you are directly saying n is greater than equal to 3. From there, this assumption hold true at the last line also.
Yes, correct. So you can also just assume that if you are assuming this condition, okay, n square is greater than equal to 2n plus m. If you are taking this condition, and you can directly replace by this, so this condition directly become like 2n square plus 2n plus 3 is always be less than or equal to 2n square plus n square 3n square. Correct? I'm just replacing this term by n square. So now I can say that this condition will always be true if we just consider this condition with this.
Correct.
Correct, na? So we are just trying to figure out the same things in the we are just expanding the our equation, and we are just trying to figure out this. So we can also do this. Okay. 1 second, someone is raised the hand.
Yeah, that is
Yeah,
me.
Ravi. Yeah, Ravi.
Yeah. Now, when we actually do this entire thing,
Hmm.
why are we actually limiting it to only 3n square? Even 4n square is going to be greater than
Yes.
that, right?
Yes, we
So
can do.
there is no limit on what
Yeah,
g
upper.
of, yeah.
Yeah, that I'll also explain that. So because according to the Bigo condition, if you see this graph, okay, so condition is only represent that condition is only represent that this CGN, okay, CGN it should be greater than or equal to Fn. This condition should be true for any value of so this n is greater than or equal to n naught. So this is the n naught point. So you can see this n naught point. So before this is representing input. Okay, this n is representing input. So here this is the 0. If we are increasing the size of input at any point of n naught, after that you can see this CGN part is always greater than or equal to this Fn. This is not coming below than, but before that it may come lower than. So after n naught point, so this n naught is representing some input value, input size. After that, this CGN function will always be either greater or equal to with this Fn. If we can prove this condition, then we can write our complexity with big O notation.
Okay.
Okay.
Now in this scenario, there is a n naught before which this thing is not
Yeah,
valid.
yeah,
After
not
that,
valid.
it is.
Yes, but
But
after that, always CGN should be always be in the upper case, upper side.
yeah. So if I take 5n square, if I take 6n
Yes,
square,
yes,
it is going to go
all are
higher
the
and higher.
correct. Yeah, all are the correct.
Sir, we will take minimum limit now, means upper limit we
Yeah,
will take.
we will take the closure things.
Yeah.
Okay, as a complexity, we cannot write the complexity in the any higher terms. So we will just try to figure out the complexity with which is a closure upper bound. We can say that.
Okay.
Okay.
But there is no definition for n naught per se.
Yeah, no. So, but this n naught should be greater than equal to 0, not greater than equal to 0. Okay. So let me just complete. Okay. So here after two terms, so I have taken two condition here. So this is the first condition. This is the second condition. After that, what relation I'm getting? Must I remove this? What happened? Okay. So yeah. So what relation I'm getting? So this is 2n square plus 2n plus 3. This is less than equal to 2n square plus 3n. This is less than equal to 3n square. Okay. And here condition I am using n is greater than equal to 3. And here I am using condition n square is greater than equal to 3n. Correct? Two condition I am taking for this. And this is the one single term which we have calculated. And we can compare these terms with CGN. Okay, where C is 3, okay, 3, and Gn equal to n square. Okay, C is the constant term 3, and Gn equal to n square. So this is the another function 3n square. And what common value we can take? So what is the n naught value here? Okay, so what is the n naught value? We can just figure out this. So any value which satisfied both condition. Okay, any value of n. So after that, if we takes any value of n which satisfied both conditions, so we have two conditions: n should be greater than equal to 3, and another condition n square should greater than equal to 3n. Okay, so any what value actually satisfied the both condition? So if you take n equal to 1, so it will satisfy the both condition? No.
No.
Okay, similar 2 is also not satisfied the condition. Okay, 2 is not greater than. But if I take 3, so 3 for n value 3 is satisfying the above condition also, and here 3 square, okay, and 3 into 3, this is also true for 3.
Can you repeat this part once again, please?
So actually during the process, when we are just reducing, when we are just figuring out the CGN part, we take two conditions in this process. when we just convert this first line to, we have written this line. Okay, so we take this condition, n is greater than equal to 3. Okay, this is the first condition. If we are taking n is greater than equal to 3, we can write in this manner. So after that, we convert this 3n function in the terms of n square. So we have taken this n square is greater than equal to 3n, this condition. Okay, and after that, we have written this final equations. So here, this is the fn. Okay, this part is the fn. Okay, and every time we are taking this condition less than equal to or less than equal to, and this is the cgn. Correct? C equal to 3, and this is the gn part. So we can, so we have proved this fn is less than equal to 3n square. Correct? So this function is actual fn, and this is the cgn. So fn is less than equal to cgn. We are just trying to prove this part. Okay, so here c, we have calculated this constant part, and gn equal to n square. But this condition should also be true for n is greater than equal to n naught, according to the graph. Okay, so now what is the value of n naught? We are figuring out what n naught value should be there. So during this process, we take two conditions. First condition is this, n is greater than equal to 3, and another condition is n square is greater than equal to 3n. So if we pass n equal to 1 in this both two conditions, so are these conditions true? Both conditions are true? Not. Okay, so 1 is not greater than equal to 3. Similar to 2 is also not satisfying the first condition, so no need to check second. If we are giving n equal to 3 input, so first condition is true because 3 equal to 3, and second condition is also true. 3 square is 9, and right side 3 into n, 3 into 3 is also 9. So both are equal. So both conditions are true. If I take 4, so first condition is also true. So first condition will always be true after 3, including 3. Okay, so 3, 4, 5, 6, this first condition will always be true. Similar manner, this second condition will also be true for every value of this input after 3, including 3. Okay, so if I take n equal to 4, so this time you are taking 4 square and greater than equal to 3 into this 4. So this part is less than to one part of this. This is 4 into 4 and less than equal to 3 into 4. So this is the fixed part according to our condition, and this side you are increasing. Okay, so this will always be greater than. So we can say that for n naught we can take 3. So for any value n is greater than equal to 3, okay, this function condition is satisfied. Both condition will be true, and this condition is now true. So if you pass n not equal to 3, you can directly compare this. So do not confuse this. So 2n square plus 2n plus 3, this is less than equal to 3n square. Okay, so we are just trying to figure out this. Just pass n equal to 3 in this function. Okay, so this will become 3, 9 and 18 plus 3, 6 plus 3, and here this side 3 into 3 into 3, 81. Okay, so less than equal to this is 18, 16, 24, 27.
That is 27, isn't it? Not 81.
Yeah,
it's
sorry, 27.
Yeah,
that's correct. Okay, so now both are equal, but if you change this equal to 2 and equal to, if you pass n equal to 4, then you will get for 16 and 32 plus 8 plus 3 is less than equal to 4 into 4 into 4. This is now 64. This is less than equal to 40 and 43. Correct? So you are getting this. This is the upper bound term. If you are taking n equal to 3 or any value after this 3. So this CGN part, this is always be greater than or equal to the actual Fn. We can write. Okay. So now we have proved this for all the constant terms. So this is the C value. We have find out this C value equal to 3. Gn value we have n square, and n naught value we have 3. Okay. Now if we have proved this condition, so this is the required condition for the big O notation. So we can write our complexity Fn equal to big O Gn. So what is the value of Gn? N square. Okay. So n square. So n square we can write. So this is the representation notation we can use for the complexity big O n square. But this is the one possible solution. But we can also write this. So this our fn function is also true for 4n square. Okay, because if I'm taking 3n square c equal to 3, so this condition is true. But we can also write 4n square. So for this 4n square, this big O condition is also true again. Okay, so 4n square, 5n square, or also you can say that nq you can also take. So fn is less than equal to like nq, or like 2nq, like this. Okay, so this condition is once again, this is also upper bound. Okay, so this is also a satisfied condition according to the big O definition. So you can also write the complexity for fn equal to big O n3 for this same function. But because this is satisfying the condition of the big O, okay, and this nq will always be the upper case, or we can say the worst case situation. But we always try to figure out the closure upper bound. So closure upper bound is here is big O n square. So according to the definition, all are correct. We can write the complexity for this function is big O n square is also correct, big O n q is also correct, big O n4 is also correct. Okay, so any value which is greater than this, we can say that all are correct according to the definition of rule.
So is there a possibility that there is not going to be any unique value for n0 if multiple people calculate the same thing?
So if what we are trying to say is just figure out the closure upper bound. What are the closures possible?
Okay.
Okay, just not just randomly figure out that if you're finding this is also true, this is also, just figure out this is correct, because we are figuring out the closest time which actually our algorithm takes in the worst situation, maximum. Okay, so that closest time we are figuring out. So for suppose this linear search, so maximum time is like big O n. Okay, n comparison is required to search. But according to the complexity, we can also write n square. Okay, because this omega notation definition is actually correct for this n square also. But this is not the actual complexity, closure complexity or closure upper bound. This is also proving the correct scenario. So this is also true. So we will figure out this n as a final worst case complexity. But we cannot write closure, smallest one. So suppose if any algorithm is taking like n time, we cannot write the complexity big O log n. This is not possible. If we are writing the complexity with big O terms, so that means this is also representing a upper bound, or we can say that the worst time. What is the maximum time algorithm can take? So this should not be smaller than the actual function. Okay, actual function which algorithm is actually taking. So what actual function is fn. So that value should not be smaller than the fn. If you are writing
where is the log n coming from? Sorry.
So I have just written a random example. If if algorithm is taking, suppose fn equal to n plus 5 like this, so we cannot write the complexity like this log n term, because this is the fn, and we cannot prove this fn is smaller than or equal to this gn. This is not correct. Okay, so we cannot write the complexity like this big O. Okay, so condition should be satisfied. Fn should be less than equal to cgn. So that if you can prove this, then you can write with omega notation.
Sir, why we don't compare only direct functions? Like why we are taking out complexity? We can compare direct functions to each other.
Where?
Sir, we can compare two function.
Yes, actually, according to the definition of big O definition says that if you can prove this situation, fn equal to less than equal to cgn, okay,
no sir,
and for any constant value of c and n is greater than equal to n naught. So this is the definition of the big O notation. So
yes,
you
sir.
have
Sir,
what you're asking.
Sir, I am saying that like the function was 2n square plus 2n plus 3. Sir, why we take out complexity? We can compare directly the functions like 2n square plus 2n plus 3. Then we will get better results.
No, so that is not the case. So in the industry, uh, if you write an algorithm and it is saying 3n squared plus 5n,
Yeah.
and another algorithm is says 2.79 n squared and 4.2 n. So people if start doing like this, so this ON is actually giving you an approximate bound. It is not giving you the exact bound, and that is well accepted in the industry. That I take it now like that.
Hmm. Yeah, this is correct because we are not calculating the exact upper bound or lower bound here. Okay,
Yes.
we are calculating the approximate bound.
Okay, sir.
Okay, so but to use notation, you have some proof to write the to prove this type of things. Okay, so fn should be less than, because you have to calculate the upper time. Upper bound means upper maximum time for the algorithms. Your algorithm should take the equal or less time for each type of input, but not more than that.
Okay, sir. Got it.
Okay,
Thank
so then you can use this big O terms with the big O gn.
you. Okay, sir.
Okay, so this is one proof. So you can use big O gn. So most of the time, so after figuring out the complexity, most of the time we use this big O notations with the complexity, but you should know the other notation also. So another notation is this omega notation. Okay, and omega notation condition is if you can prove fn is less than sorry, not less than, greater than. Okay, so greater than equal to cgn. So here this cgn part is the lowest, or we can say that the best time of the algorithms and the minimum time for the algorithm for any input. So your algorithm will take the minimum this cgn time, but it may take greater than this, but not less than this. Okay, so this c is a constant, gn is the another gn is the function, and same things, and not is greater than, sorry, n is greater than equal to n naught. Okay.
So
Yes.
if we
Would
take
be,
the
sir?
previous problem and we solve it,
Uh-huh.
basic 2n square plus 3n plus 3 is not going to change, correct? Because there is nothing called a best case scenario there. It's all mandatory conditions.
Yes, correct. So but we can prove this. This is the condition for omega notation, best case things.
Okay.
Okay, but if I'm writing this 2n square plus 2n plus 3, so this is the actual fn. Okay, so fn equal to this function, this is the actual fn. But can we say that because we are just this gn is not the exact thing, this is the just figuring out the lower bound or upper bound. Here we are trying to figure out the lower bound now. Previous we figure out the upper bound, maximum time, this time minimum time. So can we write this function like this will always be greater than equal to 2n square directly?
No, sir. And sir, one more thing. When we say O log n, we mean big O log n, right?
Hmm? Yeah, big O log n.
Oh,
That is used as a big O, and this is called as a omega, and another is theta. Okay, big O means upper bound, omega means lower bound, and theta means tightly bound. So these are the term actually we used. Okay, so why we cannot write this? For every value of n is greater than equal to
1.
1.
Yes, we can write it, sir.
Yeah, we can write it now,
Mhm.
because if we are passing any value of n is greater than equal to 1, so this part will always be greater than, because you are just not taking this 2n plus 3 in the another part. Okay, so we can write this. So now we have just reduced the function in the terms of cgn, so this we can compare with the cgn. So this is the actual function fn, and we can say that this is a equal to cgn. This is the omega definition. Okay, and here c equal to 2, gn equal to uh, n square, and n naught value is 1. So all things we have just calculated, and now this condition is also true. So if you figure out the lower bound, then you can also write the complexity with omega notation. So this notation is, now you can write the complexity fn equal to omega, what is the gn value is omega gn. Okay, so this is n square. So this is the another representation for the complexity omega n square. Okay, so if you see the definition or graph for the omega, you can see CGN is coming lower the Fn after n naught point.
Okay, I probably will ask a very fundamental question.
Mhm.
2n square plus 2n plus 3 is greater than 2n square plus 2n plus 2.
Hmm.
So why don't we use that? We want to take the highest order. That's the reason why
But
we are
still,
actually.
to represent the, because Gn, we are just calculating the term with the highest order of n. So if you are writing this like as a 2n square plus 2n plus 3 is greater than equal to 2n square plus 2n plus 2, but still you will take only highest order of n, only n square.
Okay. Okay.
Okay, so we are just reducing this complete function in the terms of CGN, where C should be some constant and Gn should be the highest order of n term.
Okay. Okay. Clear.
Okay.
Thank you. Thank you.
Yeah. So if you can prove this, then you can write your complexity with omega notation. Omega, okay, omega n square. And tightly bound is the combination of both. If you can prove, if you calculate C2GN, okay, C2GN is the upper bound maximum time. If you can calculate the C1GN, this is the lower bound. Okay, so both we have calculated for the same function. So for omega we have calculated upper bound, and for omega, sorry, big O we have calculated upper bound, omega we have calculated lower bound. Now both value we have, then we can also write the complexity with theta notation. So if you can prove both omega and upper bound for any function, then you can also write your complexity. So that means what is the condition for this theta bound is your actual function fn should be greater than equal to c1gn, okay, and less than equal to c2gn, okay, where c1 and c2 are some constant and gn are the function, and same things, n is greater than equal to n naught. If you can prove this condition, you can also write your complexity fn equal to theta gn. Okay, so both we have proved. We have also proved this condition, and we have also proved this condition in the previous two situation. Then we can also write complexity fn equal to theta. So theta n square. Theta is representing tightly bound. So that means your function will always take the time between this C1GN and less C2GN between.
Hello, sir.
Yes.
Sir, which one we choose? Left hand side GN or right hand side GN in the FN?
Both will be the same.
No, so in the previous
No,
question,
GN was same. You can see here we have calculated GN equal to n square, and the previous also we have calculated GN equal to n square.
But it is a very bad algorithm.
okay.
Okay.
But
Okay.
sir, okay, fine.
So if you are only able to prove the upper bound only, so you can write your complexity omega only. Okay. If you are able to only prove the lower bound, then you can write your complexity with omega. Sorry, previous is big O, this time is omega. But if you can prove both upper bound and lower bound, and your solution will always take the time in between this upper bound and lower bound, then complexity can be written with theta notation, tightly bound. Okay, so these are the notations, but most of the time we will always use this big O, because our aim is here to reduce the worst case time. Okay, so if we can improve our worst case situation, then that means our algorithm is better. So we will always use this big O notations for the complexity. But these conditions you should know what are the conditions for each. Yes, what are the conditions for fn, theta, omega, and yes.
Sir, can you give an example of fn where worst case function and the best case function are different, unlike in this example that you just explained?
In sorting algorithm, we will see this.
Okay, sir.
Okay, sorting algorithms. We have one insertion sort algorithm. If you have already seen the algorithm, so insertion sort algorithm, worst case time is n square. Okay, we will discuss this. Okay, and best case is
Constant.
not constant, n.
Sir,
Okay,
it can be constant or not?
no. How you can sort the n elements in
No,
constant time?
not in sorting, but like if we are selecting first
Yeah,
element.
searching. Yeah, searching. You can maximum time is n and minimum time is 1.
Okay. Thank you.
I'm just giving example for sorting algorithm, insertion sort. So insertion sort takes n square times in worst case, maximum case. Okay,
Okay.
but best case is also there if your input is already sorted 1, 2, 3, 4, 5 like this. If you are giving this type of input to the algorithms, then your algorithm will take only n steps.
Yes.
Okay, so this is the best case. So here, this is the difference. Okay, n square and n.
Okay, sir.
Similar for the quick sort, worst case is n square, but best case is n log n. Okay.
Can you
Okay, sir.
explain the theta once again, please, if you don't mind?
Theta.
Yeah.
Theta is if you can prove both upper bound and lower bound.
Ah, okay. Not
Okay,
just one.
then you can also write with theta notation.
Okay.
So these are the notation we generally use, but most of the time we represent the complexity with big O, which represent the worst type. So after so this is the representation. Now these are the common complexity actually we found for any algorithms. So these are big O1 is represent constant time, log n represent logarithmic time, n represent linear time, and this is also given in the increasing order. Okay, so 1 is the smallest one, log n is the next smallest, n is the next time. Okay, linear time, n log n is the linear take time. Okay, n square, then n q, then 2 to the power n, then n factorial. Okay,
So in this, right, one question I have: where does log square n fit in?
sorry, log square.
N. Where does it fit in?
Yeah, log square will fit in after this log n.
No, no,
Or
no. It is log n the whole square. Log n into log n.
so you are saying that log square n.
Yeah, log square n.
So that will come after this log n.
Okay.
Okay, so in between this log, or we can say n, you are saying that is square like this. Okay, so this value is actually greater than this log n, but smaller than this n.
Sir,
Okay,
which function, sorry, which algorithm have constant time? Can you give some example?
constant time. Okay, so some you will learn some algorithm in
So
suppose in
dictionary.
dictionary is also one example
So
where you can
see,
you can
let's
calculate
take the
some.
example sum of n numbers. Okay, there are two. So let's say you have to find the sum till n. Okay, there are two ways to do it. You can write a for loop and then add. That will be order of n. Or you can use the formula n into n plus 1 by 2. If you use the formula, then it has
Yes,
only one calculation. So the
constant time.
algorithm, second algorithm will have order of 1. The first
Yes,
algorithm
No,
will
but
have another order of n.
time will depend on input, right?
yes,
If
we
it,
No.
represent this time in the terms of input size. Okay, we represent this complexity in the terms of input size. So what input we are taking for the algorithms, we represent the this complexity in that terms.
is there any algorithm, sir, which take constant time despite of
So
any input we give?
yes, searching algorithm in the dictionary. So someone is have already taken this example. So
Okay, sir.
dictionary, you will just see some algorithm, some operations in the week 3. So we will use one new data structure, linked list data structure. Okay.
Sum of n natural number can also be done.
Sum of n natural number. This what is the sum of 1, 2, 3 like this. So you can also calculate by some formula like this, n into n plus 1 by 2 like this. Okay. I think this is the correct formula, or n into n minus 1.
It's n into n plus 1 by 2.
Yeah, it's correct.
Huh.
It's correct.
Okay, so if you want to add first 10 natural numbers sum, okay, so 1 to 10. So one thing, you can just run the loop 10 times, add every element, and other things you can directly use this formula and calculate. So this is the constant operation you can use in your code.
Okay, sir. Got
Okay,
it. Thank you.
but otherwise sometimes you will also figure out that some operation, if you are performing with like stack or queue or linked list, so that operation can be performed in constant time. directly in 1 or 2 steps. Okay, so we will see some algorithms where you can figure out this constant time operation. Okay, so these are some common complexity and which is given in the increasing order. So this is simply you can observe these things, which value is greater, which value is smaller. Okay, so log n is smaller than n, so you can compare these terms. So next thing is yeah, calculate the complexity. So some example is given here. So now just tell me what complexity you can calculate for this. So we will not always calculate the function, so like which we have calculated in the previous. Just figure out that if you are using the all constant operation. So let me just discuss one by one. So this is the first example. Okay, so if you run this algorithm, so here a value is given, b value is given. If you are given any value of this function, so if you change the a value and b value, so all the steps will change, number of steps will change.
No.
No, this code will always run only these 4 steps. Okay, so we can say that this code is not dependent on the input values of a and b or any things. Okay, this is simple statement, and only 4 statement will execute for every types of input. So these are the constant operations. This is one operation, this is one operation, this is one operation, this is one operation. So total 4 operation. If you are getting any fixed value, then you can write the complexity with big O 1. Okay, and also one things, you can just calculate the complexity part wise of your code. Suppose one part of the code and one block of the code is written like this, and after that, after completion of this block, you are writing another block. This is the second block, and this is the third block, like this. Okay, and all blocks are separate. Okay, so after completion of the first block, second block will start. Okay, and after completion of the second block, third blocks will start. So in that case, you can complexity in the part wise. Okay, so you can just figure out that what is the complexity for only this first part. Okay, suppose this is big O 1 constant time. What is the complexity for the second part? So second part complexity is like this, big O n. And what is the complexity of this third part? Is if all parts are not dependent. So this is big O n square. So in this case, if you find what is the overall complexity, this will be the max of all terms. Okay, n square or n or 1. What is the maximum term you are getting by in this code? That will be the overall complexity. So you can represent overall complexity by n square. So no need to just check the complexity of the whole code if code is long. Just figure out that how you can separate the code in different parts, and then calculate the maximum, which part taking the maximum. Okay, and represent the complexity in that term. So here, first example,
O1.
O1. Second example, so you can see here one n value is given. So if you change this n value, this loop execution number of instruction will change. Okay, so if you pass this n equal to 10, only this 10 times the second will execute, and 10 times third will be execute. Okay, so we can ignore the constant things. Okay, so here I am not just counting the termination 1 steps. So approx n times this line number 2 will also run, line number 3 will also run. Okay, 10 times. So just figure out that this is a single loop. If you are giving n equal to 10, 10 times this loop will run. If you are giving it n equal to 100, so 100 will time will this loop will run. So this loop is dependent on the value of n. So here we can say that what is the relation of the complexity. So this is a constant time. Okay, this part is only taking 1 step, but this is a dependent on the input and will run big O n. Okay, so this is directly dependent on the input size. So if you are giving any value of n, this loop will run that time. So overall complexity is n. So now next is this second loop. Okay, so we have already calculated this. So here this is the constant operation. If you check, this is the constant operation, but this is the interdependent. So this is the one loop and this is the nested loop. Okay, so in this time, so for each value of I, this will run n time. Okay, and we have n value of I, so this means this part will run n squared time. Okay, so this is the maximum amount if you are taking nested loop. and both loops are dependent on the n same input n. So you can say that the overall complexity will be n into n square. Okay, and you can represent the complexity big O n square. But also check both loops are running on the same input size. Sometimes this type of code is asked actually, but suppose for first loop is running I equal to 0 to n. Okay, but second loop inside this first loop, second loop is running like this. We are using one while loop. Okay, so while loop we are using, and we have initialized j equal to 1, and condition we are taking 1 is less than equal to n. Okay, so this condition we are taking, and inside this loop we are incrementing our I equal to I into 2 like this. Okay, so here this is also a nested loop. This is first loop. Inside this, for every value of I, this part is running. But also see that how the inputs are actually increasing or decreasing. So if input is this loop variable is incrementing by 1 steps, okay, so that is actually linear operation. But here what is happening, j value, sorry, this is j variable. Okay, this j. Yeah, j variable is start with 1 value. Okay, 1, and every time you are multiplying by 2, so one value will become 2 after 1 multiplying, then it will 2 into 2, it will become 4, then 8, then 16. So this j value is incrementing in this manner, and you will reach till this termination condition in how many steps?
Log n.
Log n steps, correct. So if you are taking 64, suppose this n value is equal to 64, so this first loop will run 0 to 63, okay, 64 times, n times. But inner loop will run only, so every time for every value of I, this will start from 1, and then 2, then 4, then 8, and then 16, then 32, and then 64, and will terminate. So how many steps you are using? Only 1, 2, 3, 4, 5, 6, 7. Okay, so 7, or we can say that log n step. So log n step value is represented by 8. So this is closure then.
Can you explain this part, please? I saw the video, I was not able to follow it. How are we getting the log?
So how much steps are required if you are multiplying the value every time, if you have doubled the value every time? So if you are starting j equal to 1, and each iteration when you are entering inside this while loop, and this j value is multiplied by 2 in the previous value, so this value is doubled every time, and this we are taking this condition j is less than equal to n in termination condition. We will run this loop while j is less than equal to n, and every time we will increment our j by after multiplying by 2. Okay, so initially j was 1, then it become 2, then 2 into 2 become 4,
8,
then 8,
okay.
then 16, then 32, and then 64.
Right.
Now this condition will break.
Right.
Okay, so only these number of iteration is required to break this loop. So these steps are not equivalent to 64. Okay, so this is not a linear actually loop. This is a logarithmic loop. So here this is only running log n time. So log base 2 and 64. So we can write 2 to the power 8. This is 8.
Yeah.
5.
No, 2 power 6 now.
6, yeah, correct. Sorry. So 6 times. So you will get 6 times.
So for the whole algorithm will be O n log n.
So for one step of I, log n time. Okay. Similar to second step, log n time.
Okay.
We have total n step. Okay. So
n
if you
into log n,
multiply
okay.
n into log n, so total time is n log n for this.
So sir, if I do it multiply by 3.
So that is also similar, but in that case we will just figure out this log base 3n. But this is log 3 base 3n is also considered as a log base 2n. You can mathematically prove that. So you can convert some constant part to just make equivalent. So log, if you're getting any value with different base, log 3n, log 4n, so that will also be considered as a log 2n. And in complexity term, if we are using log, so always consider as a base 2, not 10. So sometimes maybe you can consider as a base 10. Okay, so in complexity terms, we always consider as a base 2 log. So if you are multiplying by 3, that will also be considered as a log. Okay, because the log 2 is a small amount is greater than compared to the log 3. So we can also represent the complexity with log, basic log in the upper bound. Okay, so also just figure out that how your input actually this variable of the loops is dependent on the input, and how that variables are actually incrementing or decrementing. So this is also important. But if your variables are incrementing by simply one value every time, so that is actually linear things to consider as a similar. So now in the next example, in
So,
this
sir, I have a weird question. So, suppose the outer loop is in log n and
hmm,
inner loop is in something n.
hmm,
So, how
same
easy
thing,
the okay, same thing will happen. Okay,
same thing, so log n into n.
okay.
Yeah, so log n into n or n into log n, both are the same.
Hello, sir.
Yes,
When something is multiplying, then we have to take log n.
multiplying also, figure out that how you are multiplying that. Maybe you are multiplying by the 50%, so then it will become only half a constant operations, so not always case. Okay, so just check how value is incrementing. It is incrementing by 2 steps every time, so 3 steps every time, like this. So you can consider as a log n. Or same for the division also. Okay, so if you start for suppose in the same loop, if I write this uh, reverse case. So for one loop is running I equal to 0 to n minus 1, and inside this loop if you're writing one while condition and you are starting from j equal to n. Okay, and inside the while condition you are taking if j is greater than equal to 1 this time. Okay, and inside the while loop you are now dividing the value j equal to j divided by 2, or floor division by 2, like this. Okay, so this is also is similar. This time you are starting for suppose n equal to 64. This time you are starting from 64 and you are dividing by 2. So 32, then 16, then 8, then 4, then 2, and 1. Then after that this will become 0, so this condition will terminate.
But sir, for this to be applicable, we should multiply or divide by in a uniform pattern, right?
Yes, uniform pattern. So you can, if you are dividing by 3, so that will also be considered as a log, because you will get log base 3n. Okay, so that is also
Yes.
equivalent to the log base 2.
Sir, in lecture, week 2 lecture, lecture number 3, sir was saying that we don't take n, we take digits of n if we are taking fn.
That is based on the algorithms, or what you are figuring out the input, what input you are considering.
Yes,
Okay, so this is based on the problem. So sometimes maybe you have more than one input for the algorithm. So
yes,
you can represent the complexity in the both terms. Suppose if you have two types of input, like one is n and another is m. You have two lists
yes,
for any algorithms, which one side first input list size is n and another list size is m.
yes,
Okay. So complexity can also be represented in the both terms. So maybe complexity can represent it like n plus m. You will see this type of complexity in the graph algorithms, n plus m. Maybe this n into m.
No, sir. Means in sir was saying that we take the we take n
So that
plus
is
digit.
depends on the problem actually. If you are just performing some operation which is actually performing some things based on the digit, then you will consider as it input size is number of digit.
Sir, so how when we divide n by 2, sir, so how it depends on digit? I was not getting it.
So let me, I'm just giving one example. Suppose if one uh, question is given, like one input is integer value is given, like 1 3 5 4 2 8. Okay, this
Yes,
n value is given, and we are asking that how many digits are there in
yes,
this.
sir.
Okay,
Yes, sir.
so what you can do, you can perform some reminder and this
Yes,
type of
right.
operation, and then
Yes,
you will get digit one by one. So you have to run that while loop for the each digit wise. So after performing one division operation, you will get one this reminder part 8,
sir. But
like this next.
but if we divide it by 2, sir, we are not taking out one digit, we are dividing it by 2.
No,
So
no,
No,
it's
Length is
divided by
shrinking, right?
10 here.
no, yeah, you are right. Means if we divide it by 10, then we take the digits. Okay.
Yes.
But if we divide it by 2, then why we take digits? Sir was saying if we divide
The
it by,
length will shrink, right? So if it is a longer
yeah,
number, then the length
Uh,
will also shrink in order
so
with like
here
by 2
this
by 2.
number of digits are 1, 2, 3, 4, 5, 6. Okay, so
yes,
your loop should be run 6 times at least. So every times what you will do, you will just figure out the last value. So after dividing by 3, you will get the remainder 8. Okay, but you have to convert this number into a smaller after removing this. So you have to divide this, and you have to just take the qs and that part only. So that how you will get after simple integer division. So 1, 3, 5, 4, 2, 8. So for reminder you will perform this operation.
yes, sir.
Okay, 10. But how you will get the remaining value, you will
Divide
get
by
1,
10.
3, 5, 4, 2, this floor division
Yes,
by
sir.
10. Then you will get this value.
Sir, but if we divide it by 2, then we will not take n as digit. Am I right?
No, why you are dividing to according to the problem? There's no meaning to divide by 2 here.
Yes, sir. But if there is some other problem in which we are,
So that depends on the problems. What operation actually you are trying to do by dividing by 2. So
oh,
this is one
like
example
we are
which is
halving the
depends on
number.
the input length actually.
Yes,
Yeah.
sir. Here we are
Uh-huh.
taking out the length, but if we are halving the number, then we will not take digit as n.
That is not depends on the digit there. If you are performing any division operation dividing by 2 and you are not figuring out this length of the, so actually I am just figuring out that how when the this algorithm is dependent on the number of digit, because this is a
Yes,
integer
sir.
value, this is a
What?
integer value, and
Yes.
this is a very big value. But what problem is we are figuring out how many digits are there in this.
Sir, at last of this session, sir, we can discuss the lecture number 3.
Okay, that's the
So
last
I
one.
have a doubt in this question.
Huh?
So, for calculating any big of something, we have to check just like we divide and multiply. We have to check just like it for calculating for big O of something.
No. Here, what we are trying to do, we are just figuring out that how our problem is dependent of some input, and we are figuring out that what inputs we should take for this problem. So we cannot say that this problem here we are counting the digits for this given value. So this value is 1, 3, 5, 4, 2, 8. Okay, so this is one integer value for n. So we cannot say that this our algorithm will take this amount of time. This amount of time. Here our problem is different, and problem is actually counting the number of digits. So we can consider the number of digit as an input, not the value of n. Okay,
Okay, sir.
so we will consider represent the complexity with the terms of number of digit in this. So we will consider if we are giving n equal to 10, so we have only 2 digits, so our loop will run only 2 iteration. But if we are passing this value, so that will take 6 times. So our number of operations are depends on input number of digits here. So we will consider number of digit as input for the problems.
So
Okay,
here for the number of digit finding, it is a ON problem.
this will not represent in the terms of n then.
But number of digits
A
is
number of digit, if we
this.
consider as a digit d, so if we are considering the number of digit is d, so we can represent the complexity big O d.
Big O D, correct.
Not
Now,
n.
sir, can you give an example of ON plus M?
Yeah, that type of algorithm will come in the graph mainly. So where you have number of vertex. Okay, 1 second. So suppose you have number of vertex v equal to n, and same times you will also get information number of edges. So we will consider as m. Okay, number in our graph how many vertex we have, how many edges we have. Okay, at that time you will get some operation, some algorithms which will dependent on the both information, number of vertex also, and okay e. And similar time one example you can take 2D matrix. Okay, suppose if your matrix size is n into m. And if you want to traverse all the element, okay, if number of rows are n, number of columns are m, if you want to traverse all the elements of this 2D matrix, so how much time you will take in the terms of input? Here input is represented two dimension, n and m. So n into m operation is required to traverse all the elements.
Okay.
Okay, so here input is given in the two different dimensions. So like what is the number of rows and number of columns, and your total number of operations are dependent on this multiplication n into m. If your number of rows are 4 and number of columns are like 6, so how many elements this matrix will contain? 4 into 6, 24. 24 times you have to visit the elements. You have to visit all the elements row wise and complete all that. So your operations are dependent on the multiplication of rows and column. Then you can represent your complexity n into m.
Okay.
So input is dependent on the problems. So if you are giving some input list and your algorithm is dependent on the input list size, so you can consider as input list size as a input n. Okay, so that input you have to decide what term actually you want to use as a input, and your algorithm is directly dependent on that.
Okay.
Okay. Yeah, someone is asking. Yeah. Yeah, Karthikeyan.
We are trying to explain this complexity based on big O, theta, and then there is one more three. One is on the upper, lower, and tight, right?
Yes.
In that, when the lower and this tight will be more useful to give the complexity based on
This
the lower and
depends.
tight.
Yes, in some problems, if you are not able to figure out the upper bound, actually, there's no, you cannot prove or calculate the upper maximum time for the algorithms. So at that time, if you are only able to just figure out the lower bound, what is the best case time is required by the algorithm, but you are not able to prove that what is the maximum time. So in that case, you can only represent with your complexity with omega notations, because you don't know what is the upper bound of the algorithm. Algorithm can take any time. Okay, but tightly bound, if you have proof for what is the maximum possible time and what is the minimum possible time for the algorithms, if you know this, then you can write your complexity with theta notation also. So suppose the sorting algorithms. Okay, so insertion sort algorithms, you know max this minimum time is n. Okay, and maximum time is n square. So you can also represent the complexity theta n square for the worst case, theta n square, or similar things for the merge sort. Merge sort always takes n log n time. So you can you know that maximum is also n log n and minimum is also n log n. So you can represent tightly bound theta n log n. So this is just a representation. So most of the time we will just try to figure out big O notations. Okay, but if you have no information on, you cannot prove the upper bound, then you can represent your complexity with omega. Okay,
Sir,
yeah, Vivekanand.
And sir, should we have to remember that certain type of algorithm is the big of this?
Certain type of algorithm
Means we have to remember the you have big of any square is the applicable for this algorithm, and
So yeah, for some standard algorithm, suppose if you are learning the sorting algorithm, you should know what is the best case complexity for insertion sort, what is the worst case complexity for this, but always use the big O notations, no problem. Okay, so don't confuse with this another notations like omega or theta, but you should know the condition for that, when we can use the omega and when we can use the theta. But most of in during the whole course we will only use the big O notation. Okay,
and for sir, and for every equation we should remember that the that equation is big of n
no, no,
square
no,
and big of.
every equation you no need to do after some maybe after some calculations, so you have to figure out that So you, by looking the loops and this iterations, most of the time, and if your code is normal iterative code, not recursive code, then you can directly figure out the complexity by just looking the loops.
Okay, sir.
Okay, and the loops, and sometimes this login is also included based on the incrementing or decrementing condition. So just after some figure, if you see some example, so maybe just always when you are writing the code, then just figure out that how your input size is dependent on the number of operations by looking the that iteration. Okay, most of the time iteration is required.
Okay, sir. Thanks.
Okay, so
So,
yes, Rohini.
so I have one question. If we have 3 or 4 assignment operations, and then it is followed by some for loop, the number of assignment statements, how much space will it take according to BIGO notation?
So
So
this
we have 4 assignment
Mhm.
statements.
Inside the loop.
And how much? No, outside the loop.
So if you are just as I have explained the first example, so this is the constant things. Uh,
Huh.
so the first
So
example.
suppose after print we have a loop. The
Huh.
4 assignments or 3
Okay,
assignments and
okay,
1 print.
okay.
That will be, we are writing it as O1, no?
But this will not
So that
affect.
whole thing is, this will not be O4 or something. It is
No, no,
just
no, 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 no,
O1.
no. Actually, because of that, I'm saying if you have some sequential part of the code. Okay, so suppose if you want to start same code, let me just. Suppose this code is written. After that, just this code is also written. Okay, you are saying.
Okay.
Okay, so this is a constant operation. This is also a constant. This is also a constant. This is also, and this is also constant. So this complete part is a constant operation. Or
Yes.
if you count this, this is a 5 steps. So this is a constant value, and this
Yes.
will not change for
Yes.
any input size of n here. Okay,
Yes.
but after that, this loop is starting. But this is depend on the input
Yes.
n. So this part is
Yes.
actually taking big O n.
ON.
Okay, or this part is, we can say that this is constant operation. So what is the maximum value
Okay.
of this part?
Okay.
Okay,
Okay.
big O n.
Okay. Then it is O of N. Big O
So
N.
one example is remaining, so that will clear these things. Okay.
Thank you, sir.
I think someone is raised hand. Yeah, Vivekanand Utkars.
So, can you explain the example for log n, just like a 2n square plus 2n plus 3 you have explained?
Log n.
Log n, for log n. How
So
can you track the
binary search algorithm is actually the best example for this. So during the binary search explanation, I can explain that. It is fine because the binary search is also in the part of Week-2.
Okay, sir.
Quick question: will the OPP questions be as tough as the GRPA questions, or easier?
Some questions will be easier, okay, but similar to your GRP or practice assignment or live coding assignment, similar. But in OPP exam, actually we gave some easy problems. Maybe 2 problems are easy, but 2 are moderate type. Okay, but questions will be very similar to your that assignments problems. Okay, so we will discuss these things, and we will also release the mock questions, so you can figure out the labels. Yeah, Utkarsh?
Sir, I missed the live coding one session. Can I get it
Yeah,
on YouTube?
it is available on the YouTube.
Okay, thank you.
Okay, just see the calendar. In the same calendar event, the YouTube link is also added.
I'm unable to access the Replit.
Replit, you have to join the Replit. Otherwise, you can see the all problems on the portal also. Okay, so portal
Okay.
inside the live coding.
Portal, yeah, in the portal I saw, but it's
No,
not, I'm unable to access the.
you have to join the Replit team by the invitation link, and we have pasted this. We have just shared this link in this inbox today. I have just shared this one announcement. So here you can see this Replit team for live coding invitation link is given. Okay, when you click on this, you will directly join the Replit team. Okay, where you can see that all live coding problems of week 1.
Sir, there are two questions,
Last
7 and
7 and
8.
8. Yeah.
Sir, I am not able to do that questions.
Yeah, that problems are actually challenging problems. So I'm not
Sir,
supposed to every beginners can solve that problems. These are competitive problems.
where can we find the solution of these two questions?
Solution we will release after live this week 2 live coding. We will release this solution.
Can you
Sir,
kindly share
sir,
this link to this
sir,
Replit?
So
so,
I have
sir,
one problem about graded programming assignment 2, means week 2. In week 2 graded programming assignment, what I found was we have that input statements at the bottom, no? In graded week 1 assignments. But in week 2, we don't have those input statements and print statements. And then in the first problem of graded week 2 programming assignment, the first problem, it says you have to define a function combination sort. And when I try to write the main program, it is not calling it is giving some error. And how do I take the input from the screen which is given?
Okay.
in that you just have to
Could you
define like a
just
normal function, def, then the function name as assigned to you in the
combination
question.
sort? I defined the function combination sort with string list, but how do I call it from the main program? That is what I was like. You have to pass on the string list to the main program,
Yeah,
to
one
the
second.
combination sort.
You no need.
You don't have to call the function. The portal will take care of it.
Let me share that question. So what is GRPA 1?
Graded GRPA 1 of week 2.
Huh.
Yes.
So actually, question statement is this.
This combination sort.
So just read the problem statement. What the required function you need to write? Okay, so here you need to
Write
write.
Python function.
You need to write only this
So we have
function definition.
Okay.
Some part is also given in this code, but that is hidden actually.
We don't have to write that part.
You no need to write
We
any
just
other
have to
part.
write we have
Function
to
only.
write only the function part.
Function definition. Just write
And
the
then
function
test
definition
run.
and what return things it is asking. So this function should sort the list and return two lists.
Sort the list.
Okay.
Yes, yes.
So that
Okay,
should be satisfied by
So
the
while we are here, can you check PPA2 because on selecting language in PPA2, it is getting disoriented in my portal. The whole layout is getting disoriented after selecting P.
Oh.
Sir, when you scroll down, you will see a lot of the large numbers as in test case 3.
Okay. Okay, that I will check this. So are you getting any this type of problems with?
Yes, sir. Is sir scroll down a bit?
GRPA I'm asking.
No, sir, not fit GRP, only PPA2 for now.
Okay, one second. Yeah, so you can see this large test case is coming, but this is coming as a lower things. You can just scroll this. So the size of the test case is big because
So
of that.
that's how the portal is already test cases given to us, or is this an error?
No. There's no problem with the okay with the code or anything, but this is just a layout problem only.
Okay.
Okay, if you are so are you able to figure out the problem statement now? So problem statement.
I will zoom out it a bit.
But I think this is just a new problem for us. So we will check this with the ops team.
Where is this Replit questions from the portal? How to go there?
So on this menu, when you click on this, there's one tab in the last after supplementary content, live coding section is there. Okay,
No, but
when you
but
when you
but
click on
live
it,
coding is having some questions we just have to solve here, right? We don't have to go to Replit and do, sir,
no,
right?
no, actually during the live session we use the Replit team.
Okay,
Okay,
so
but
whatever questions here, because I didn't attend the live session,
ha,
so
ha.
whatever questions here, we just have to solve, right?
Yes. So actually, it's the same problems we are releasing on the Replit during the live session. Okay. So some this time also 6 students are trying to solve these problems. Okay.
Okay.
So 6 problem we have released and two extra. These last two are the actually challenging problem. So
But this 7 and 8 is not available in the.
yeah, our portal we have not released because that problems is actually competitive problems. So
Oh,
maybe
okay.
many of you are not able to solve that because that are actually mathematical tricky. You have to figure out the logic, then you can directly solve. That problem is
And
not too much difficult, but some mathematical logic you have, need to apply.
sir, now while we are at the end of the class, may I show the doubt in the PPA one?
So in this case, how to go and see the problem 7 and 8 for those who
So you
did
can
not
open the
attend?
Replit team. If you have you joined the Replit team or not?
No, I have not
Yeah, I
joined.
I just sent the invitation link in the chat.
So if the time permits, if you can explain problem 7 and 8, like I
Uh,
was not getting the question.
I think it will take more time. So I think you can discuss this problem in the next live coding session, or
Sir,
you can
can
discuss this problem in the TA session.
sir, can
Because
you take up PPA one now?
okay, PPA one.
Actually, it is saying in my scenario not able to run the code. I wrote two different
Yes,
codes,
it
and
is for
sometimes
me
it is
also
saying
not
not
able
able
to
to
run.
run, and sometimes it is giving the wrong
Can you
output.
share your code in the chat?
Yeah, yes, in the chat, or should I present the screen?
Just share the code. Then I will just
Okay, sir.
show you. Okay. Yeah, Vivekanand.
So
Sir, the
how can
comment.
The Replit invitation which you have sent, it says you have to log into your account. The
Yes.
account username will have to be your
You have to create.
um,
You have to create the account on the Replit. You can create by your student email ID or your personal ID. You can also use. So we are not restricting
personal
any
ID.
student ID, but just try to create by student ID so we can also see the record.
Which
sir?
student ID we have to create?
You have, I think, only one
Okay.
student ID, no?
Yes, yes. Sir, but I have still not
So
received
it's a
the
wrong code.
identity card for
I will paste another.
diploma.
You have not received, but I think you have received your email, na? Email ID.
Email ID I have, but that small ID card which we have to show at the
Okay.
time of
So I think
quiz,
for that
the,
you
that
can.
has that has to have that diploma thing instead of
Okay.
foundation level. So I received the new one with foundation level only, not with diploma level.
Okay. So that I think you can write to the support
So I
regarding
wrote
this.
I
about
have
this to
already
support, and
written
they
to the
said it will
support
get
team, but they
updated.
have not yet replied.
Sir, they have replied to me and said they will update within few weeks.
So actually they are working on that because in the initial of the course, so they have lots of work to set up all the things. So that will take some time. Okay. So just wait for that.
Okay.
Sir, I have pasted the code.
ES
It's
dot
too late.
study, no?
That the same.
ES dot study.
Okay. PPA 2, week 2. Where is the PPA 1 or 2? 2.
PPA1 of week 2. In this question, sir, I also had a doubt how to keep track of the count variable to check the number of times I have validated the k value.
Okay, so I think
Using global.
I have already posted the solution of this problem in the discourse. If you have not checked, I have posted the solution of recursive as well as the not non-recursive solution. But one important thing which I want to just say that if you are writing the solution for the log n complexity for any problem, so okay, so if suppose a problem is asking for the solution of log n complexity, and you just figure out that you have to use binary search. Okay,
Yes, sir.
So do not use the slicing in the implementation.
Sir, but this question didn't specify that. It was another
But
question
do
that.
not do this type of practice. Otherwise, in the OPP exam, maybe you can write this type of code and you will not able to pass the test case.
So can you just test it, because it was saying sometimes it was getting run and sometimes it was saying not able to run.
Okay. So, but this is the recursive code first. Okay.
Yes.
And okay. So this is not the correct because you are calling recursively this code every time.
Yes.
So every time this count is a new variable for the each call.
Yes, I got it.
Okay, and every time this will initialize with 0 and it will increment by 1 only. So this value is not
Sir, why?
reflecting in the overall result.
So I have an alternative code also. I defined count in the function itself after k, but that too didn't work.
So if you want to write the recursive solution for this, so you have to use the separate function. So
Okay,
let me
sir.
just show the solution code. But this code is not correct.
Okay, sir.
Okay,
Sir,
because counter will not be
I was
incrementing
facing
correctly.
trouble although with the count concept, but my main issue here is that the portal isn't able to run. It is showing not able to run as a summary.
Because maybe your code is not stopped. Let me check your logic also. Okay,
Or
otherwise.
maybe recursion depth.
And regarding recursive calls, the portal is restricting us to pass the arguments. So it is very difficult to do some recursion as per our convenience. It is
PP1. PP1. No?
So he had just asked another question. I also wanted to get the answer for that. The thing is, sometimes when we run the code, we get a message that says not able to run. And it's not like a runtime error or wrong answer or anything like that. So what do we understand from that? Sometimes the code is correct, but when I run it twice or thrice, it runs, and otherwise it shows not able to run.
Yes, sir, because if it would be recursion depth, it wouldn't be able to run every time, but it is running sometimes and not sometimes not.
Okay. So actually, we figure out these things in the previous terms also. So sometimes what happen? One possible reason we figure out that if you're copying the code from some other documents or some from other source, if you're not writing the code, if you're copying the code and you're pasting the code directly here, so some Unicode character actually added in the code that is not visible, but that actually create the problems during the running times.
Okay, but
At that time, this is not able to run error is comes actually.
Not
okay,
for
so
this
actually I was working on Jupyter Notebook and then I copied it onto the portal. Maybe that's why. But the same code, like I don't change anything, I don't backspace or anything, and then I run it twice or thrice, it starts working. So,
So this is not the case for always, but this is one case we found that in some
Sir,
problems when the Unicode is actually added.
sir, but if for in my case for this question, in my portal I wrote it all without copying and pasting, but then also it was showing not able to run sometimes.
Sometimes, okay, but
Yeah.
it is running sometimes
Yeah,
also.
after 2 to 3 attempts it run.
So maybe the server issue then. At that time, maybe some portal issue or
Yes,
server
sir,
issue.
I'm also having the same problem. I'm running right now. I wrote the code. I didn't copy from anywhere else, but
Okay.
it's showing.
Can you share your code if you're getting the same error right now?
Yes,
So
sir.
I
Yes.
just tried. I am also getting same with this code only.
Sir, will I share?
Not able to run.
Yes, sir. This problem.
Okay, let me check what mistake maybe there. Okay, so by research you are writing, you are taking the length, then left and right 0 line -1. Middle calculating, check equal to false, count equal to 0. If L is equal to empty, return false and count. If this condition is true, count equal to return true and count. Less than K, count plus equal to 1, return while search index comparison. L middle plus 1, Okay. Okay, else count plus equal to 1 written by Mrs.
Sir, will not the recursive call will initialize the count every time to 0 in line 6?
Yeah, that logically this code is
This
incorrect,
is
but
not
we are
correct. Yeah.
talking about the
Yeah, why
total error.
code is not running actually? I'm just checking. This is not able to run. Why this is coming?
So you can try clicking twice or thrice, it will run automatically. That's the main error. Same code without changing anything. It was this error was in the Python also. Last time I pointed out to the TAs that time. The same error was in Python file handling week.
We're getting the same error. Okay, this time wrong answer. Yeah, correct. Okay. So okay, I'm noting down this code. 1 second. I will check this. I will send this with the developer teams. So why this coding is creating problem? Any other solution code if you're facing the same?
So I mean any code that I'm writing in this portal, it is showing this because I wrote an alternative code also, and that too was showing the same error. Shall I paste it too?
Let me just try run this code because I have written this code recursive. This is also a recursive solution, correct solution. Let check it this. Okay, so first explain this solution, how you can use the counter if you're writing the recursive binary search. Okay, so what you can do, you can define one function binary search separately. Okay, and you can read the output what binary search is returning. That means element is exist or not.
Okay.
But before this function, you are just using one global variable count equal to 0, and inside the recursive function. So this is the recursive function. Okay, inside this we will just make this count as a global variable, and we will increment by this one.
Okay.
Okay, now this count can be accessed by this binary search, and because we are just mentioning that this is a global variable, so we will increment this value, and that value will be reflected in the output every time. So if you are calling recursively function, this value will be incremented by 1 every time for every recursive call. Okay, so what we are doing, we are just passing the first call for this separate binary search function, and after that this output will get only true or false. Okay, element is exist or not, and this count value will be incremented for the every call. So this count we can directly print here, count.
Okay.
In the recursive call, we are taking this as a base case. If our high is minus low is less than equal to 0, so then we can directly return false. Otherwise, we are calculating the mid index. So according to the problem statement, this condition is given. Then we are simply checking if element is matched, then return true. If not matched, then we are just setting mid minus 1. If it's smaller than, otherwise we are setting mid plus 1, like this. So this is simple binary search algorithm. Okay, then we are using this counter here. So let me check this. This is running. Yeah, correct. This is also, I'm getting not able to run. Yeah, this is, I think, something new problems with the server, because I have already tested this problem on portal before.
Answer
Step
for
fast.
the answer for the topics that are left in the for the today's class, like the sorting methods and the searching. Will it be taken in the next session or?
No, I think no, but so if you can stay, I can also just take 30 minutes, and then we can cover. So that algorithms is not too much.
Yes, sir. I had a doubt in the merge sort function.
Okay, so yeah, I'll check this problem. So this is issue with the portal, not with the code. So I will just share with the developer team.
So even I am having problem with the portal.
No, if you are getting this not able to run, so this is one problem.
No, if when I run first time it says 0 out of 4 private cases are successful, and
Mhm.
second time without changing anything it is giving 2 out of 4 are successful.
So that is actually
Whereas in the
because
public cases, no, public cases all are clear.
so because what is the actual reason is this, because your code is very closer to the efficient code, but not better or exact required solution. Okay, so sometimes that code actually pass the test case, sometimes not, because just try to improve the efficiency of the code little bit more. Okay, then code will be passed. So that actually required time to validating this type of code. Actually we are comparing the actual system time, computer time. So if your code is very closer to the set time, then it may pass, sometimes not pass, but so we generally gives greater time. Okay,
Oh, the time constraint is
yeah,
there
time
also.
constraint is there. Just try to improve your code little bit more, so then you will pass.
Of in even in our graded assignment also it is there.
Yes, so I think some problem is there. So like let me, this is not dependent on this combination grp2. So this code is actually based on the log n required complexity, grp2 required efficient solution. Okay,
So
and
can you go for GRPA 3? 1 second.
yeah,
Yeah,
grp3 is this.
GRPA 3, right? The while loop that I am unable to execute even the simplest of the while loops in the function.
A while loop.
Yeah, I'm just trying while or a for to see even len of this thing is not coming. Len of the list, len of my list is not coming. So it's not. I'm unable to print anything.
Okay, yeah. So this is problem is just configured in the different way. So you cannot access the list directly, because this list is just configured in the class forms. Okay,
So how are
just
we? How?
just follow the problem statement. Here some fixed instruction is given. You can only use this swap of function, which is already defined in the as a hidden or prefix or suffix
Yeah,
code.
I agree that. I agree
Okay,
with that.
but do
The
not try
thing.
to do any direct access or direct operation on this. You cannot
No.
perform.
So we cannot see. Let's say we say a of I used to read element at index I, right? Okay. So for that we need to go through each of the element in that list. Correct.
Hmm. But
So
what
I
problem statement is saying that you can only use these operations,
yes, I am
swap
only
operation.
using those operation. I'm not. I'm unable to use either for loop or a while loop or any kind of loop over
You
there.
can not. You can also not access the element by the index.
No, we can, right?
So let me just read this. Given a custom implementation of the list name, my list, on my list object, you can perform read operations similar to the inbuilt list. You can use AI. Okay, you can read. Fine. To read element index I in my list object A. The only possible operation that you can use to edit data. Okay. Yeah, you can read the element in this manner. A, I, and yeah.
So if I use a for loop, it should iterate through the list and it should print the index. It should print at least print the elements, if not anything. Correct?
Hmm.
It's not doing it.
Okay, but what the return statement is asking, because this is the required function merge in place.
So the return function does not. We don't have to do anything. We just have to
Okay,
keep
same list. Okay,
just
same
simple
list.
return. We just have to do a simple return.
Mm-hmm. So complete the Python function merge in place, except two my list A and B containing integers that are sorted in the ascending order. So let me just check. So this is the required function merge in place. Merge in place. Sorry, I'm writing C syntax. Okay, so let me print of A0.
It started working just now because for like just 10 minutes back it wasn't working. At this point it is working. The for loop is working in the code.
Working.
Yeah.
Sir, merge M is missing.
You're not able to run. Okay, so we are getting this problem. I think this is something new problem. I will discuss this problem with the devs team, so maybe they will resolve this very soon.
Yeah.
Yeah, this
Thank
is
you.
okay. Okay, so just try to cover the remaining things quickly. So now complexity part is covered. So yeah, one more example in the last. So here, if some code is given like this, okay, so this is the combination of the complete code which I just explained that. Uh, so you can see this is the mixed code, and here you can see that this first part, okay, so this first part is completing, after that second part is starting. Okay, so that means this part will complete and then second part will start, and then we will not never back to the first part. Okay, so we can just separate the part wise. So suppose you can separate this first part as like this, this is the second part and this is the third part. Okay, this is the third part. So what is the complexity for the first part is, you can write big O n, because there is one loop, for loop. In second part we are using one nested loop. Okay, so both are running n times, so this is order of n square, and next loop is the 3 times nested loop, so this is order of n cube.
N cube.
Okay, so overall complexity will be the maximum terms for this. So this maximum terms will be considered as a overall complexity big O n cube for this complete code. This is the complexity. And sorry. Yeah, recursive part. Recursive is also important, and some algorithm we will just some method we will learn in the week 8 for this. Otherwise, some simple substitution method you can use. You can explore the terms. So what is this recurrence relation, and what is how we can calculate the complexity for the recursive functions? Okay, so recursive function means if we are calling the same function from inside the function. Okay, so that is called as a recursive function. So here you can see that this is a factorial program, and inside this program we are calculating this, we are calling this same function inside the function. Okay, this factorial, this is the same function we are calling, so this is the recursive function. So how we can calculate the complexity for this type of function, this type of recursive code? Okay, so in that case we write the recurrence relation for the recursive code, and what recurrence relation is actually represent this recursive call structure. So total time tn. Okay, so this n is representing the same what input we are giving n. Okay, then second term is, we will just write that for every call how many times we are calling the same function and what input we are passing. Okay, so we can say that this overall tn is the combination of t. Okay, so we are calling this function only one time from here inside the function, and we are passing input n minus 1, so we can see that tn minus 1. So this is the next call of the same function. And apart from that, if you just ignore this part, apart from that, what amount of time your code is taking? Okay, what is the complexity of the remaining part of the code? So this is a multiplication operation. Okay, so this is a constant operation. This is also a constant operation. If you are checking simply, if you're comparing the element and return the element, this is also a constant. So overall, the remaining part is taking constant operation. Okay, so we can write this constant like plus 1 or sometimes big O 1 like this. Okay, so both are okay. If you're writing 1, okay, so this is the recurrence relation for this factorial code. This is representing that the main time is Tn, but inside this time we have to calculate the Tn minus 1 first. Okay, and base case is also, every recursive function also contains the base case, okay, to terminate or just stop the recursive calls. So this is if n equal to 0. So this is a one time condition that will be satisfied every time we are decrementing this value by 1. So at one time you will reach this if condition statement, and at that time this recursive call will stop. So that is one constant operation. So we can say that for fixed value n equal to 0, that loop will stop. So at that time, if t equal to 0, then only constant operation is required. This is return statement. So this is the base case. Okay, if we are giving n value, this is the required time, Tn minus 1 plus big O 1 constant. If we are giving n equal to 0, then only one step is required. This is return statement, okay, without any recursive call. So this first part is actually represent the recursive calls, number of recursive calls, how many times we are calling the same function recursively, and what is the time for that. And this is the time apart from this recursive call, what code is taking time. Okay, so this is called as a recurrence relation for the given solution. Okay, so this is the main recurrence relation. This is the base case, t0 equal to 1. Now how you can calculate the complexity if you have recurrence relation. Okay, so now after recurrence relation calculation, you can calculate the complexity. So we can just expand this. So Tn, if you have, then Tn minus 1 and constant time I am writing. Okay, so if I just replace this value n minus 1, Tn minus 1 I am writing here. Okay, so just replace all the place n by n minus 1. This time we are giving n minus 1 input. So what recurrence relation will be? Tn minus 1 minus 1, correct? Plus this is fixed part, constant time. Okay, similarly this will become n minus 2, and we can also write t, if we pass Tn minus 2, then you will get Tn minus 2 minus 1 minus 1 like this. Okay. Okay, so we will always just replace this n by 2 in this n. Okay, so this will become like n plus 1. So in this manner, we can write the complexity, and what we can do, we can just expand the overall equation. So overall equation is this like this. So Tn equal to Tn minus 1. This is the first. Okay, now we can replace this by this line. Okay, so Tn minus 2 plus 1 plus 1, correct? Now we can replace this part by the lower part, this one. Okay, so this is n minus 3. So Tn minus 3 plus 1 plus 1 plus 1. So what relation you are getting? Every time you are decrementing this n minus 1, n minus 2, n minus 3, and also you are getting some fixed operation 1 plus 1 plus 1. So you can write like this as a Tn minus 1 plus 3. Sorry, n minus 3 plus 3. Okay. So to reach at the base case, so if you just if you want to remove this recursive call, so you have to satisfy this base case. So that means this n minus 3, this inner part should be replaced by 0. So after n iteration, so what we can do, we can write like this Tn minus n. So you can see we are getting the same value which is coming as a subtraction at the here, total number of operations 3. Okay, so if we reduce n, so we will also get here n. Okay, in that case, so Tn minus n will become 0 plus n. Okay, and this T1 T0 is 1 operation, unit operation. Okay, so 1 plus n. So overall time is required n for this, and we can write the complexity big O n. Okay, so this is the substitution method. You can expand the expression by putting the value for each recursive call. Okay, and after getting some equation, you can just solve that equation by mathematically, and you can get the complexity overall value. Otherwise, one another method we will discuss in the week 8, that is called as a recursion tree. Okay, we can just calculate the complexity graphically, that I will just explain with some example of merge sort or binary search also. Okay, so any query in this? So this is recurrence relation. Now we will just check the sorting and searching algorithms now. Hello, am I audible?
Yes, sir. No doubt.
Yes, sir.
Okay. Okay. So next part is let me just move to the. So I will explain this merge sort complexity later, and searching algorithm. So these are very basic algorithms. So when you are learning this type of algorithm, so also figure out the small that cases. Okay. So for linear search. So linear search, you know that we are simply comparing element one by one. Okay, and we will start from the first element, then we will compare if our searching element is matched, then we will return the answer. Otherwise, we will move to the next element. So this is very basic approach and naive approach, we can say that. And this takes best case 1 and average case big O of n. Sorry, worst case is big O of n, but average case is also actually if you calculate the all possible case. If element is exist at the first position, second position, third position, so if you calculate the average, you will get n by 2 value as a average. But to represent the complexity for n by 2, so that will consider as a you have to ignore the constant part, lower part, and then that will be considered as a big O of n. Okay, so we can also represent the average case as a big O of n. So this is the basic first, then binary search. Okay, so binary search algorithm, you know the concept that actually applicable only the list if the list is in the sorted order. Okay, or sometimes we can also write the similar type of implementation if you know the pattern of the elements. Okay, if you know the pattern of the elements, so you can also write the similar type of binary search implementation to solve that problem in log n time. Otherwise, the main binary search algorithm is actually a algorithms that is applicable on the sorted elements. You can, if a list is already sorted in either increment or decrement order, so you can apply this binary search method. Okay, so what is the algorithm is? So if elements are sorted like this, so 1 2 3 4 5 6 like this, an element. Okay, so you know the element are arranged in the increasing order. Then what you can do, if you're searching like where is the element of 6? Okay, so no need to compare from the starting right now. Okay, so you no need to compare from the starting, directly check the middle element. Okay, directly calculate the middle index. Suppose if you have 100 elements in the list, and figure out what is the elements that exist at the 50th index. Okay, so 100 by 2, 50 index. So what element exists at the 50 index? If that element is matched with the searching element, so you can return the answer. Yes, element is exist at this place. But if not matched, then you can check the searching element is smaller or greater than the middle element. And based on that, you can discard half of the problem. Okay, suppose if you are searching like 6 and you are getting middle index as a 5, so definitely 6 will come after this 5. Okay, because the elements are arranged in the increasing order, so no need to check the first half now, and you can completely discard this part. Okay, so that problem size is decreased just in the half times. Okay, initially we have n elements, now we have only n divided by 2 elements to search. So in that way, every time just repeat this process, calculate the middle index and compare the element. If not matched, then check it is greater or smaller, and based on that, just reduce the half size of the searching. Okay, so every time your problem input size is reducing by half. So in that case, if you initially have n element, next iteration you will only have n by 2 elements. Okay, next n by 4 elements. In that manner, your searching area is reduced. So you will reach at 1 in log n steps. After dividing by 2, n by 2, n by 4, n by in this manner, so you will reach at the one element when only one element is remaining. So total number of steps is required log n. Okay, so you can find any elements in log n steps if you follow that approach. If your input elements are arranged in the particular order, increasing or decreasing, so you can apply this binary search algorithm, and this is very efficient for the large input. Suppose if you have 1024 elements, so this is very large number of amount. If you apply the linear search, so for maximum worst situation you have to traverse 1024 times, but in binary search you have to just traverse log n time. So log n time value is very small for this 1024, so this is 2 to the power 10. So that means you have to compare only 10 elements to find out any elements in which exist in this 1024. Okay, so 10 comparison is required, 10 steps you can find any element by using this binary search. Okay, so this is the concept of the binary search. If you know the concept, then you can implement these algorithms. Now for the implementation part, actually professor is explained in the lecture that slicing implementation. Okay, so this slice that is, I think, this one. Okay, because most of the time this course is actually taught in the C and C++ in this type of language, so that slicing is not there. So but in Python actually this is introduced. So professor at that time also professor just ignored these things, but this operation is actually this slicing operation internally takes n time. Okay, because what is this meaning of slicing is, if we are passing this L slash mid this type of parameter, so that means one new list is created, and all half of the elements 0 to mid, all elements are copied from the current list to the new list. Okay, and so suppose if you have 100 element and if you're passing this type of slicing, so that means 50 elements will be copied from this first list and new list will be created, all elements will be copied to the new list. So 50 times new operation will be performed internally. So that 50 n by 2 is also considered as a order of n time. So that is also a linear operation if you are copying half of the elements from one list to another list and creating new list. So that operation is a linear operation internally. So sometimes if you write this type of code using this slicing, so this may be not able to pass the test case because your code is not you are not achieving log n complexity for this code by this code. Okay, you are following the approach correctly, you are just finding the middle index and you are comparing the element correctly, but this only this single operation is taking order of n time. So now overall complexity will become order of n for this implementation. Okay, so just try to ignore this slicing from the binary search code, because here our main goal is to find out just achieve this log n, but this operation is taking n, so you cannot achieve. So what you can do, you can simply ignore this and you can write the different implementation without slicing, and either using the iterative method while loop, or maybe you can also use the recursive solution, but you can pass the parameters. So let me just show you the implementation. So these two implementation are given, iterative implementation. So here what we are doing, we are simply taking list and searching element, and we are calculating the low index and high index. Okay, last index and first index. After that, we are calculating the middle index, and we are using only while loop. Okay, we are not calling recursively this time. We are calling the middle. We are calculating the middle index. We are comparing the element. If elements are not matched and greater than, searching element is greater than the middle element, we are setting our low at mid plus 1 because mid is not matched. Okay, so at that time we are setting mid plus 1. If our searching element is smaller than middle element, then we are setting our high index to mid minus 1. Okay, so by setting this way, we are reducing the half of the size. And otherwise, if both conditions are not true, that means our element is matched. Okay, so we are returning mid. Okay, so if we run this loop, so we will get our solution in some place. So maybe if we are getting, suppose if our element is exists, then we will return the mid index. Otherwise, if this loop is completing without any this return statement, so that means our element is not exist. We have checked all the middle element. Now our element is not founded. So at that time, return statement, this last line will be executed. If this return statement is not executed inside the loop, then last return statement will execute, and that is returning false. That means element is not exist. So you can see that only log n operation is performing. We are reducing the size by half every time, and we are returning the answer.
Will this work for both odd and even numbered lists? I mean, number of
Both.
elements. Okay.
Yes, yes. This will work for every. Okay. And another is implementation is the recursive implementation. So this is recursive implementation, but you can see this time we are not using slicing. What we are doing, we are passing the same list parameter, okay, L. So this is indicating to the same object which we have just received as a input. Okay, this name is directly pointing to the same object. Without, this is not creating a new object. This is pointing to the same object. But what area we need to check in the next recursive call, that we will decide based on this two parameter low and mid minus 1. So we are passing these two parameters in the call, that will decide that we need to check only this range low to mid minus 1 in the next recursive call. Okay, so these two parameters we are adding in this recursive call. So you can see this is the base case. If this condition is satisfied, we will return false. Otherwise, we are calculating the based on this high and low value which we have received first time. So first time we will pass 0 and the last index of the actual list, but in the recursive call this value will be changed. Okay, so if this value is matched, we will return the mid element. If the searching element is smaller than L mid, okay, middle element, then we are calling the same function. We are passing the same list, okay, searching element, and low index is we are not changing because our element should be come in the first half, okay, and we will ignore the second half. So we are setting our end, okay, so this high value we are replacing by mid minus 1. Okay, so that means second half is now removed. So this parameter we will pass, and now this low will become same, and but high will become mid minus 1. So that part will only be accessed in the next recursive call. Otherwise, we will pass in the different way. So here we are passing the parameters, or parameters are representing the index to search the next part of the same list that will decide. Okay, so this is the recursive call without using the slicing operation. So by this implementation we can achieve log n time. Okay, because all operations are now okay. So this is binary search. So now you know that complexity is log n, so just remember these things. And we are performing in place, we are not using any extra space for this binary search. Here we are using extra space, okay, because we are creating this list every time new list. So this new list is created, okay, so that means we are incrementing our space in the every call. We are creating new list, copying the element, and then we are, so this slicing implementation is taking more space also. Now sorting algorithm. So purpose, you know that we have some random order, we want to sort the elements. So this is the main purpose of this. But for the selection sort algorithms, so according to the algorithms, so what is the main idea of the selection sort is, so we have random element like 2, 5, 4, 3, 1, 6, 8 like this, okay, and in the list, and we want to sort these elements using the selection sort algorithm. So according to the name of this algorithm, selection. So every iteration, so okay, so first we will point out this the location. So That means, so after sorting into the increasing order, our order should be come in this manner, like 1 2 3 4 5 6 8. Okay, this is the correct. So that means first place the smallest value should come, second place the next smallest value should become in the sorting order. So same concept we will use. We will just point out the first position, and we will iterate the complete list, and we will compare the, we will check what is the smallest element. Okay, so we are pointing this first location now, and we will compare. So we will consider that this is a minimum element initially, and after that we will compare all the elements which are remaining after that with this element, and if any element is smaller than this, so we will just say that this, now this is the minimum. Okay, and in this manner we will figure out the smallest element for the first position, and after getting the smallest element index, then we will swap the element. So this is the approach for this. So for first position, that means smallest element should become. So we will come. We will just consider this is a minimum. Minimum now equal to 2. Then we will just check 5 is smaller than minimum. No. 4 is smaller than minimum. No. 3 is smaller than minimum 2. No. Now 1 is smaller than minimum 2. Yes. So now we will set our minimum to this position. Okay. And next 6 is minimum compared to this minimum. No. 8 is minimum to 1. No. So finally, one iteration we get this position where we have the smallest element. Okay. Now there is one pointer we have set in the starting, where we are actually finding out the correct element for this position, and we will swap this minimum index and the current position. Okay, swap these elements. So after one iteration, you will get 1 5 4 3 2 6 8. Okay. Now just shift our current pointer to the next position. Okay, so now this position, now this part is already sorted, so no need to check this part. Okay, now this is the second position element. Same process repeat again. Okay, just find out the minimum element in this part only. Okay, what is the smallest element in this part? So just come assume that this is the minimum, and after that compare the element. So 4 is smaller, yes, so now this is the minimum. Okay, now 3 is smaller than, yes, this is the minimum. Okay, 2 is the minimum compared to this, so now this is the minimum. Okay, and 6 is not minimum, yeah, it is not minimum, so yeah, this is the final smallest for this part. And swap this element by this position. So 1 2 4 3 5 6 8. Okay, now this part is sorted. So in this manner, for we are pointing out the position, and after that we are finding out the correct element for that position, which should come at that position. Okay, by simply comparing the element. In this manner, all elements will come at the correct place after all the complete the iteration. So you will get the shortest list. So now you can see in this process, this is not depends on the input type. Okay, you have to repeat all the operations. Suppose if you are passing the sorted list, so 1 2 3 4 5 6, if you are giving this input list to the selection sort, same things you have to perform all the operation. So you have to point out this, then you have to you have to check this is the minimum, and then you have to compare all the element one by one. So algorithm is actually will perform all the operations based on this according to the logic. But mainly you will get the minimum position at the same place, but you have to still compare all the element. Okay, so all operation will be performed, and this is not depends on the input. Okay, algorithm steps are not dependent on the input type, we are saying. Okay, so that means if you are giving sorted input, unsorted input, reverse input, any type of input you are giving for the selection sort, algorithm will take the fixed amount of time based on the input list size. So in this manner, this algorithm will take. So okay, so for complexity calculation, so we have n elements. So you can see if we have 6 elements, so in the first step we are comparing with all elements. So first we are starting from here, then comparing this like. Okay, so we will take total number of steps n minus 1, then n minus, in the next steps we have reduced one element. So next step is n minus 2 comparison. Next step is n minus 3 comparison, like this. Okay, So every time one steps is reduced, so you will get one series n minus 1, then n minus 2. So this is the number of operation. Okay, just add all these operations. So n minus 3 like this until 1. So you will get this type of n equal to n plus 1 divided by 2, and if you solve this, you will get n square by 2 plus n by 2, and this is the highest order. Okay, so we go n square is the complexity. So this n square is complexity for each case: best case, worst case, and average case. Okay, so all case you will get n square. Yeah, two properties also important for the sorting algorithms: this stable algorithms or sort in place algorithms. So sort in place means, are you using the same input list to sort the element without helping of the another list, another space? Okay, so that means you are performing swap operation in the same input list, and by performing the swap operations, you are getting the sorted output in the same input list. You are not using any additional list, or you are not copying the element to the another list. So like this, you are not using any additional space. Okay, you are performing the operation in the same input list. So that is called as a sort in place. We are sorting into the same input place which we have received. So yes, this selection sort is a sort in place algorithms. Yeah, stable means stable. This is a stable algorithm or not? So what is the meaning of stable? Is if you have more than one element which have the similar value. Okay, so suppose if you have like this type of list, so this type of list 1 2 1 4 2 3, like, okay, so here you can see that 1 is also exist here. Okay, 2 is also repeated, this value are repeated. So after sorting, you will get answer like this: 1 2 sorry 1 1 2 2 and 3 and 4. Okay, so now here the similar value order is changing or not. So suppose if we give some name for the similar value, so this is A and this is B for 1, and this is A and this is B for 2. Okay, so in the output list, this order should not be changed. So in the input list, this A is coming before B. So output list also, this A should come before B. Okay, for the same for 2, this A should come before B. That means order of the similar elements should not be changed in the output.
But sir, we can define the order by checking for inserting a condition like strictly less than instead of strictly less than or equal to.
But still selection sort is not stable. If you follow this equal to or less than things, still it is not stable. Why it is not stable? Because the order can maybe changed. What happened actually, suppose if I take this example, let me one sorry 2, figure out the example for this. Three. Three. 1 second. Okay. Suppose 2. So we can see that suppose if we are taking like this, so 2 comma 2 comma 1. Okay, so suppose this input is given. Okay, now you can see that this first 2 is exist at the A, and this is as a B, and this is the separate element. So in the first step, what you will do, you will just select this pointer and you will figure out that what is the minimum element. So you will find out that this is the minimum element 1, and this element will be swapped with this. Okay, so in this case, you will find out that this 2 is now shifted after this 2. So in the next iteration, you find that 1 is come at this place, 2 and then 2, and this is now B and this is A. In the next iteration, if we are not taking this equal condition less than, so this will not be replaced. Okay, so this two, if you figure out that this is the smallest, yes, this is the smallest, next is also equivalent, then you will not change. So this, so in the final output, you will see, you can see you are getting this list 1 2 2, but now order is changed. So first 2 is now shifted after the second 2. So there is a chance you will get the unstable output.
So it depends on the test case, right?
Hmm. Yeah, so if your algorithm is failed
So,
for any
so
input, that we consider
what difference does this two and that two make?
here you are not able to
Two
find
is
out any difference.
same. No, no, no. Two
Huh?
is same. No, numerically both twos are same.
Huh?
But we have labeled them as A and B.
Yeah.
What difference does it make whether this two is here and that two is there?
Yeah, so here there is no difference between the value, but some applications actually have some difference. Suppose if you have database where you are maintaining some ranking in the students, or you want to just maintain the ranking, like suppose name is given, okay. If suppose two parameters of given student name, okay, student name and marks, okay, and you want to just arrange your merit list based on the two parameters. If marks is higher, that should be come at the top. If marks are same, then order should be comes at the alphabetical order. Okay.
But then when we are sorting it over there, we can put in that condition also, no? That
That
total
condition we
marks
can
per month.
also, that condition we can also
So
use.
that will take care of this A and B.
That will take care. So yeah, that
So
we can
we
use
can have
alternate
a
approach.
complex condition that total marks also should be
Yeah. So
more.
suppose if you are given one input list where the students already in the alphabetical order, but marks is not in the alphabetical order. Okay. In that case, you can apply the selection sort, any stable sort algorithms only based on the marks list. If
Yes.
it is a stable algorithm, that order
Okay.
will not be changed. This student order will not.
Yes, yes. Okay,
Okay,
okay.
but not
Thank you, sir.
algorithm is not stable, then order will be changed. So some application is required where we just try to just sort the list more than one parameter based on that. So at that time, this stable or unstable thing is also important. So yeah, selection sort is not stable. Now second algorithm is insertion sort algorithms. So insertion sort algorithms basically the approach is, suppose some inputs list is given. So like 5 3 1 4 2 8 6, like okay, this random input is given. So what logic is we used for the insertion sort? uh, we just figure out the positions, like this is the first element. Okay, now for single element we can consider that this is a sorted element, so this part is a sorted element because there is no element compared to this. Okay, when we are just looking this. So but when we move to the second element, okay, second element, so what we can do, we can compare, we can just compare this current element to the previous sorted part of the first element. Okay, so previously only one element is exist. If this element is smaller than the this last element, because we have just considered that this part is now sorted. Okay, single element, this is sorted. Now we will compare this last element only to the last element of the sorted part. And if this element is smaller than, then what we will do, we will swap this element. Okay, now in the first condition this will become 3 5. If any elements is also coming in this part, in this side, okay, sorted part, so we will just repeat this process because the part is already sorted, previous part is already sorted. If any time we are finding out that elements are in correct order, so that means we can stop the process. Okay, we can stop the process. So let me just solve this in this manner. So in the first step, if we compare 3 to 5, yeah, this is not in correct order. Okay, so we will swap this. So we will get this list like 3 5 Now 1, 4, 2, 8, and 6. Now you can see this part is sorted. Okay, this part is sorted in the previous process. Now we are taking this element. Because this is sorted, we will compare this element by the first element in the last element in the sorted part. If this is greater than, okay, if the current element which we are comparing from the unsorted part into the sorted part, last comparison, if the current element is greater than to the last element, so no need to check for the previous elements because all are the smaller element compared to this last. Okay, so we can stop that process. But if this is smaller, so this one is smaller than 5, so we can swap this element. So in the first time this will replace by like this, so 1, 5, 4, 2, 8, 6. Okay, now we will again check with the latest element in the sorted part. Okay, so this one is also smaller than 3, then we will swap again. So 1, 3, 5, 4, 2, 8, 6. So what is the meaning is here, we are picking one element from the unsorted part and we are just finding out that where this unsorted element, this current element should be located into the sorted order, where this element should be shift or fixed to in the sorted order, and we will just insert at that correct location in the sorted part. Okay, because of that name is insertion sort. We are picking the element and inserting into the correct place in the sorted part of the part of this algorithm. Okay, so now you can see this part is now sorted 1, 3, 5 increasing order. Now next element you can see 4. So just compare this with the last element of the sorted part and check this is smaller. Yes, just swap with this. Okay, so this 4 will come here and 5 will come here. Now again check 4 is smaller than 3. No, if 4 is greater than 3, definitely it is greater than all the elements which is coming before this 3. Okay, so no need to check after that. If this condition is not satisfied, this 4 is not smaller than 3, we can stop the process. Okay, so in this manner we found that 4 is only smaller than 5, then we will only swap one operation. Then we will compare again, 4 is smaller than 3. No, then we will stop this process. So in this manner we will get 1, 3, 4, 5 and 2, 8, 6. Okay, now this part is sorted. We will pick this 2 and we'll check where this should be inserted. So this 2 should be inserted here. Okay, so by the algorithm we will just start comparison from this 5. Yeah, this is smaller. Then 4. Yeah, this is smaller. Then 3. This is smaller. Then 1. No. So we will just shift this 2 here. Okay, we will shift all element one position to the right and we will insert here. So in this manner we will get 1, 2, 3, 4, 5, 8, 6. Okay, now you can see 8. When you compare this, so this is now sorted part. When you pick this 8 and compare from 5, yeah, it is greater than 5. So no need to check the remaining element. You can stop. Okay, so just move to the next element 6. Okay, and so this is now coming in the sorted list. Compare with the 8. Yes, 6 is smaller than 8. Swap this. Okay, so 6 and 8. Now compare with the 5. Yes, 6 is greater than smaller than 5. No, just leave it. Okay, so you will get like this 1, 2, 3, 4, 5, 6, 8 sorted order. Okay, so here, yeah, so this process is dependent on the input order. Suppose what we are doing, if we are passing the sorted list, so 1, 2, 3, 4, 5, 6, 7 like this. So we will start from the second element. We will check second element is smaller than this. No, we can stop the process in the only by checking the one step. Okay, so this is one comparison. Then we will compare this 3 by 2. Yeah, this is greater than. Then we will not check with the remaining element. Okay, and we will compare 4 by 3. This is greater than. Stop. Okay, this is 5 is greater than 4. Yes, so we can stop here. So you can see this 6 is greater than 5. Yes, then here. So every time you are only comparing the current element with only the single element, previous element. Okay, so this is only one operation for each time, and your list is now your process is complete. So in this case only n operation is required. If your list is already sorted, then only n comparison steps is required to complete this process. So that means if you're picking in the reverse order, what you have to do in the worst case situation. So like reverse order is given 6 5 4 3 2 1 like this. Okay, so when you are picking this 5, you are swapping one operation, you are performing one operation, so 5 6. And when you're picking 4, so this 4 will compare with 6 and 5 both, so two operation is required in the next iteration. Okay, so you will get 4 5 6. When you are picking 3, so that 3 will compare all three elements in the previous part, so 3 operation is required. Okay, and then you will get 3 4 5 6. Then when you're picking 2, so that 2 will compare with the all elements 4, so 4 operation is required, and you will get 2 3 4 5 6. And then when you're picking 1, 1 will compare with all element 5, so 5. Okay, so these are the number of steps. If you have total number of n elements, so that means you are getting the same type of series, n minus 1 plus n minus 2 plus n minus 3 dot 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 1. Okay, and then you will get the same n square complexity.
I have a question here.
Yes.
When you compare, let's say, 4 with 6 and 5 after it is sorted, 4 compares with 6.
Yes.
And it is more, so it flips.
Huh.
And then one more time it does. This entire thing is happening in a loop, but it is dependent
Yes.
on the number of number of numbers that are ahead of it. Correct? It is
Yes,
not
yes,
n.
correct.
It is not n then.
No, no, no. So how many elements are available in the previous part, which is already sorted? So that loop will run only that time, number of
So
times.
that will
This
not
is the maximum
be.
times. Worst case, if your element is already in correct order, so you can stop that process in only one comparison, one steps.
That is the best case, correct?
Best case. So because of that, if list is sorted for insertion sort, that will take only order of n times. So now you can see the implementation. So if you see the implementation, so this is the first fixed loop. Okay, this is running n times.
Next is a while loop. Okay.
Yeah, so
got
this
it.
while loop is actually dependent on the order.
Yeah.
Okay, we are comparing the element Lj by previous element Lj
Right.
minus 1. Okay, and we are also taking this condition. We will just repeat this process if our j is greater than 0, because 0 is the last index. We cannot go further. Okay, so if we found this condition is true, then we will swap the elements, and we will reduce j equal to j minus 1. Okay, so this while loop is dependent on the order. If order is already in sorted order, so this loop will always terminate in one steps. So this upper loop will run n times, but this inner loop will run only one time every time. Okay, for the every value of I. So in this manner, you will get only n steps overall for the best case. Okay, so if you want to see the flow, then you can also just pass the value this notes, then you can verify this. Okay, so same things. Now best case is order of n for this. Average case is order of n square. We consider that. Worst case is order of n square. And yes, this is stable algorithms and also sort in place algorithms. Okay, so here the order will not be changed because we are just shifting, we are swapping the performing operation if you are getting the unordered situation. So like if we have the similar elements, so like we have given 2 1 2 3 5 like this. Okay, so first we will perform the swap operation. So this is a, this is b. So then when we compare this 1 to previous part, so that will be swapped. Okay, so 1 and 2, and then 2 3 5. Then this element will compare with this 2. This is not smaller than, so no swap operation will be performed. So this if value are similar, so that will not be, order will not be changed. So in this manner you cannot so same things if this 2 is comes at the last place, let's suppose here, so 2 1 3 5 2 like this. Okay, still you will get 1 and 2, after that 3, so 3 will not change, then 5, then 2. So 2 will compare first this 5, yeah, will swap, then will with 3, then we'll swap, but after that this is the equivalent, so no value swapping. Okay, so that will look like the 2 2 3 5. Okay, so still A and B. So similar value elements will never be swapped, or order will not be changed in this process. So here this is a stable algorithm. Next is merge sort. So merge sort is basically this divide and conquer approach based, where we are dividing the problem first, and after that we are merging the solution. So how we can just think about this, how operation are performing. First thing, you should know how the merge operation is performed actually. So if you have two sorted list, like 1 3 5, okay, so suppose first list contain these element, second list is contain this is A list and this is B list, and index is 0 1 2. Okay, so like this is the first list, and second list contain like 2 4 5. Okay, so if you have two sorted list, you can merge this list into a one sorted list. How you can do? You can just take two pointer I or J, and you can take new list like C. Okay, and just compare the element. Okay, if compare the first element and first element of the both A and B. If I element is smaller than the J element, just pass this element to the sorted list 1. Okay, and increment the counter of I, which is the smaller. Okay, I is now move to this one position. Okay, now start the comparison again. So 3 and 2, at this time 2 is smaller, so just pass this 2 element into the sorted list and increment the J counter. Okay, J will move here. So now 3 and 4, 3 is smaller, so pass this 3 and move this I into the next place. Okay, here. And 5 and 4, 4 is smaller, so 4 will shift it here and increment the J counter. Okay, now this 5 and 5 both are same, so you can just pass the same element 5 here, and this is now completed. If any list is completed, what are the remaining elements in the second list is just pass all the elements in the same order 5. So you will get the sorted merge list after getting two sorted list. Okay, so you can simply merge the list, and this is a simple operation. If this contain n by 2 and this is n by 2, so total number of operations is required maximum n. Okay, n by 2, and so total comparison is required, total n steps is required basically. So this operation will take order of n time. Okay, this is n operation. Apart from that, what we have in according to the algorithms, so we are starting from the unsorted list. Okay, unsorted list like 5 4 8 3 1 7 2 9, like. Okay, so I'm taking this 8 element in the unsorted list. So according to the problem, our problem first divide the list into two equal half. Okay, and so in the next step, so that means our algorithms will divide this list into two equal half. So 5 4 8 and 3. Okay, and next is 1 7 2 and 9, two list. Okay, after that once again,
Sir, if the length is odd,
then you can take 3 element. So suppose you have 7 element, so just use any formula for the divide. Suppose you can take n for divide by 2 like this. Okay, if this n is equal to 7, you will get 3. Correct? So 0 to 3 use in one list, and 4 to 7 use in another list. If you have even number this, so maybe one element will come in the one list, one element will be more in the another list. So there is no problem with this. Okay, because you can also merge two lists if size is different. Okay,
Yes.
so suppose if this list contain only 3 element, so like 2 4 6, and this list contain maybe 5 element like 1 4 6 8 10, like. Still you can merge.
Yes.
No problem. Okay, so yeah, so here now again divide this 5 and 4, and next list is this 8 and 3, and this is 1 and 7, and this is 2 and 9. Okay, now this is again list, but still we have two element. We will repeat this process until we will get one element in a list, single element. So 5 and 4 and 8 and 3 and 1 7 2 9. Okay, so like this. So this is the dividation process. I'm just drawing this structure to explain. Otherwise, recursive call is actually performed just that calls the function in this side first. Okay, that will not draw this type of structure, but we can draw this to understand this logic tree structure to explain this. But first, recursive call first will complete this part. Okay, then return back. Then so I will also explain that in the different way how the recursive call actually execute the process. But the same actually the problem is divided into the similar way, but not exact the same time. Okay, so that operation is actually performed in the different times. So now you can see we have only single element now in the each list. Okay, and single element we can consider as a sorted element. If we have single element, we can consider as these are the sorted list because there is no comparison. After that, we can start merging process. So now we have two sorted list which contain 5 and only 4. Now we can apply the we can call the merge function, and that merge function will take 5 and 4 and will compare the element and will return a merge sorted list, so 4 or 5. Okay, so after merging process you will get one sorted list 4 comma 5. Okay, by this merging of here. Okay, so I'm just writing m. So initial part is the merge sort m call merge sort ms. Okay, now merge function is started. So you get one merge list. Similar way from here you will get one another merge list. Okay, so 3 comma 8 after merging these two sorted list. Now here 1 comma 7. Okay, so this is 7 and 2 comma 9. So now this is the merge list after combining two sorted list. Now we have same process again. So for this merge process. Okay, now you have two sorted list 4 5. This is in the sorted order, and this 3 and 8 is also in sorted order. You can apply the merge process. So merge process will return a sorted merge list after combining both. Okay, so you will get 3 4 5 8 by merging this 4 and 5 and 3 and 8. Similar from here. Now you have two sorted list. You can merge 1 2 7 and 9. Okay, now you have again two sorted list. Okay, now you can apply the merge function on this. So then you will get this 1 2 3 4 5 8 and this 7 sorry 5 7 8 9. Okay, final sorted list. So this is the way of the merge sort, and we can also understand the execution flow of the merge sort like this. So we have one list. So I'm now drawing the structure in horizontal manner, because you know that the operation always execute in the top to down manner. Okay, so I can say that I am calling merge sort on, I'm taking all the 4 size list now this time. So 3 comma 1 4 2 like this. Okay, so this list we are calling, and this is the first call we are getting. We have more than one element here, so now we will call this function here recursively. Okay, 2 times. In first time we will call merge sort and 3 comma 1. Okay, and another function is 4 comma 2. So we have divided this one list into two lists. Okay, once again we will call this function ms function like 3. Okay, okay, we have now division process. So and this ms function on 1, and this is ms function on 4, this ms function of 2. Okay, so flow of the recursion is actually exists in this manner. So we are calling this ms merge sort function on this first list. If size of this list is greater than 1, we are calling the recursive function. So our flow will move to this top side this time. Okay, 3 comma 1. Again, this will move to this side 3. Now from here, actually you have only single element. This will directly return this element. Okay, so if you see the implementation of this merge sort, you can see the condition. If this is the base case, okay, if n is less than equal to 1, we are directly returning the list. Okay, we are directly returning. Otherwise, what we are doing, we are calling the merge sort for the left or for the right, and we will receive this. So in this manner, same manner, you can understand that. So this is the left, you will receive this result in the L, and here is the right. Okay.
Sir, may I interrupt?
Hmm.
Sir, in the here in the code that we have, the diagram that you draw, it will return 3 and 1 separately, right? And
The
when
list.
in the and when we go to the implementation, it will also say that it will return the 3 or 1, and then it will end the code, right? Can you switch the code? Huh.
Huh.
It will end the code. Then it won't go to the sorted merge list where we are calling the merge function.
No, this is the base case.
Yeah, the moment the
Huh?
base case gets executed, the whole functions get
No,
we
no. If we are returning here, so the remaining part will not be executed for that time.
so that's my question. So the merge function will also not get executed. The merge
No,
function
no.
that is merging left half and right half.
Huh. But the previous part, where from we have actually, where from we are coming actually, at that time, so we have called this function here, so we have completed this part, then we will perform this merge operation. So let me just explain completely. Okay, so this is now base case, we have reached at the base case, correct?
Yes, sir.
And we are receiving this is equal to L and this equal to R, correct?
Yes, sir.
Okay, this is R, and for this R, this is L and this is R. So our flow is going in this manner. So first, this is the main call, and we will just move to the top side first. Okay. So this L part, this is the first recursive call,
Ravi, my
because this is not a base case. So we will just call L equal to ms 3 comma 1. Once again, we will move to this side. So this is the base case actually. Okay, when we are calling this L equal to ms, so this is one recursive call ms. So what this part will return? What this part will be returned?
3.
Only one list 3. List, not 3, list 3.
Yeah,
Okay.
list 3. Okay, sir.
That list will come here. Okay. Now this L we have received. Now, so this part will be we have executed. Now we will move to the second steps of this recursive part. So this is the second call, R equal to ms, the remaining element. Okay. So this part will return list 1. Correct? R
Yes,
equal to
sir.
1. So now you have received L equal to 3, R equal to 1. Now these two operation is performed. Next operation we have written after that, merge. Okay. So in the recursive call, after two recursive function, okay, left half equal to this, right half equal to this. Next is sorted merges list. Okay. So this is the third step of this recursive call structure. So this is the third step I am writing here. Now you have received L, R, and you have both values. So you are receiving sorted list. Okay. So S equal to merge L comma R.
But sir, here's my doubt.
Hmm.
I understand that it gets what we have written, the merge function will merge the left and right. But sir, that will only get executed when the whole 3 of the recursion function will stop, right?
No, no, no.
Because recursion is creating a type of a nested environment for us.
Huh.
So,
But
but we can't implement a sudden function in that nested environment.
no,
Because
but just consider that we have started from this first call. This is a recursive call. This ms is a recursive call.
yes,
I'm
sir.
just talking about this recursive function, this part, merge sort.
Yes, sir.
Okay. So when I'm calling this function, because the list size is greater than 1, okay, base case is not satisfied, then we will call first recursive part. Okay, this L equal to merge sort, this ms. So this is the first line of the code. You can see this line only executing. Okay, this
Yes,
line is
sir.
executing. But internally this merge sort is a recursive function. That means this will execute first, this will complete first, then you will come to the lower part, because nature of the recursive call is first you will jump, first you will finish this merge recursive call. After returning back from this, once you receive this final value in the left half, then you can move to the next step. So this is the recursive call. You have to finish completely this part. You cannot directly move to second step if you have not finished this.
Yes, sir.
Once you receive the final list of which replaced by this call, and that list will be assigned to this left half, then you will move to the next part.
Okay, sir. In the nested environment, the final list that L will be assigned to the left half.
So
List L.
because of that, I'm here saying, so
Okay,
this
sir.
is the first call which we are just writing. This is the first call left. Okay, so your control will be moved to the again. So this is the new recursive function ms. Okay, now once again recursive call will be, so this new function will be executed from the starting, and definitely first recursive call will come again. So left part, okay, left part again. So at that time you will pass only this 3 element as a left part. Okay, and once you have received this, now this is the recursive function again, but now this time satisfying the base case, and you are directly returning list what you have received in the input, you are directly returning into this L. Okay, so this is the first recursive steps of this algorithm, this ms algorithm here. Okay, now if this you have received L equal to 3 here, now you will move to the second step, which is right. Okay, this one.
Yes, sir.
Okay, now from here you will get r equal to 1. Now you have received L or R. Now third step is also there. This is called as a merge. So s equal to merge. What is the current L or R is? This 3.
3 and 1.
1. Okay, now you will get one merge list that will be assigned to like this 1 and 3 sorted list.
Yes,
Okay,
sir.
so that s is now this one. So you have received here. So okay, let's see what is the next thing is in the code. Sorted list you have received here. Okay, and you are returning this sorted merge list. You can see you are returning this list. So in this manner you will return this list into this function.
Okay, sir, got it.
Okay, now you will receive L equal to 1 and 3 by this function.
Yes,
Okay,
sir.
this is complete. Similar way here, L equal to you will receive 4, and then this part is completed. Now in this part you will receive R equal to 2, and next sorted part S equal to merge. Okay, sorted merge. So then you will receive 2 comma 4, and this S will return to this function, and here you will receive R equal to 2 and 4. Okay, now this L part is completed, R part is completed, and you will call the sorted merge function from here. Okay, so S equal to sorted merge function that will take L and R as a input and will return a one sorted list. So 1, 2, 3, 4. Okay, and you will return this S to the main function here, and that function is returning this final list. 1,
Yes, sir, got it.
3, 4. Okay, so in this manner recursion is actually happening, but we can draw the tree structure to understand the dividing process.
Yes, sir.
Okay, so merge sort takes so it is also not dependent on the input order, so it will always take order n log n time. So why this is taking n log n time? So we will understand the recurrence relation for this. So recurrence relation is because if you see the recursive call, okay, if you see the recursive call, we have two recursive call. Okay, apart from this two recursive call, we have one merge function call, and this merge function is taking order of n time, combining two n by 2 list. So total time is n. So we can write the recurrence relation for this. So overall time is t n. Okay, and we have two recursive call. Or each recursive call we are passing half input. Okay, so n by 2. Okay, so this is the recursive part. Apart from that, what is the maximum? What is the complexity of overall? So that is n. Okay, so this is for merge function. So
But
this
sir,
is
for the normal recursive function, it should be n also, right? Because it is creating a new list there also. We are slicing the list,
Huh.
right?
But
So
that is not affecting the overall, because if recurrence, if you are using slicing, so you can also write n plus n, but that will consider as a 2n, but still you can write like as a overall
okay.
big N. Okay. So now this time you have one operation which is similar to your merge operation, so you can consider as a order of n. But in the binary search, actually our overall requirement was log n, but this operation was operation taking n times, so this is greater than. We cannot achieve log n then.
So this n by 2, from where did it came from?
So you are passing the half size of each column. You can see.
Oh, okay, sir, got it.
Okay, n by 2 and n by 2. Each recursive call you are passing half size of the input. So in this manner, this is the recurrence relation for merge sort, and we can see that if t equal to 1, that directly 1. We are returning the 1 value. Base case. Yes, someone raised the hand. Yes, Ravi.
Yeah. Firstly, when you showed the algorithm, you're using slicing there. So that is something which we discussed a little earlier, that slicing in itself has its own.
So but here slicing, this operation will not affect the overall complexity, because here our overall complexity is going to the above of n. Okay, in binary search, our operation should take log n time.
Right.
Okay, log n time. But if any operation in the implementation is taking n times, so overall complexity will become maximum terms n.
Okay.
Okay. Here what happening? Here we are writing this 2t n by 2. Okay, so this is the recursive call. Inside this recursive call, we are using slicing, that is taking n time. Okay, but our merge operation is also taking n times, so that is actually equivalent. Both are equivalent. So we can also write tn equal to 2t n by 2 plus 2n. Correct?
Right.
One n for merge sort and one n for slicing.
Right.
So this is a constant term, so we can ignore this.
Doesn't matter. Okay.
That will
Next.
not affect the overall complexity.
Yeah, that was my first question. The second one is, can you go back to the algorithm, the program, please, where you had implemented this?
This one, yeah.
Yeah. Here, okay. You were explaining this a little earlier. I am still not too clear. That's the reason I'm asking. Left half, you're using a merge sort, which is recursive. So it goes into recursion, and every time it goes, it only goes after the left half, right?
Left. No. So this here, first time when you're calling merge sort, this is a new recursive call when you're passing half of the left part. Okay, but at that same time, so that part will also be divided into left or right.
Correct. So
Every time we will move first left part, we will complete first, and after returning back, then we will finish.
This is where I actually am a little foggy. When we say left half is what? Left half is invoking merge sort. So let's take a list which is complete now. There is a half which is L and the other half is R. Okay.
Yes.
So we take the L, and then in the L we again go into the merge sort.
Yes.
There again I take the L. There again I take the L. There again I take the L. So complete left side is taken care of.
Yes. So that will be implemented first according to the recursive nature. So that left part, so that means first this part will complete first. Okay. This first line will be executed completely first. After finishing this part, then we will move to the right part. Next instruction.
Yeah. Here what I want to understand is, when left half has started, we go to the unit level numbers. I have the left, which is only the left side, because I'm going left.
So yeah, so once after some recursive call, you will reach at this base case. So what is this base case? If you have only length 1, then you are not calling again. Then you are directly returning the answer, this list. So at that time you will stop and you will return back to the previous call.
Yeah, I go to the previous call, but before I go to the previous call, the last left sort, the last left, it will actually not have a right.
Sir, we are going 4 left. Like if we are going 4 left, then after that we are going 3 left, 1 right. then again we are going
Okay,
to.
let me just revise again. Okay, so I'm writing merge sort in this manner, ms, correct? This is recursive call I'm writing. Merge function is different. I will just explain by m. Okay, I'm taking this input 4 1 3 2 like this. This is the one input list we have initially. Okay, and this is the first recursive call we are getting, and this is the main input list we are getting to sort. So this is not satisfying the base case because length of here is n equal to 4. So we'll move to the next call. So first steps, we have 3 steps. Okay, or we have 4 steps actually. So what steps we have? First step we have L equal to ms merge sort function again on the left part. Okay, this part only. Correct? 4 comma 1. Second step we have r equal to ms and second half this time. Okay, 3 comma 2. Next step is s equal to merge. Okay, so I am writing merge. Okay, so merge function l comma r here, and next step is return s. So this is the main 4 steps of the recursive. If you see this implementation, you can see these are the 4 steps we are using. Left equal to merge on the left part, right equal to merge on the right part, merge sort on the right part, and after receiving left half and right half, we are merging these two part and we are getting one sorted merge list. Okay, and we are returning this. Okay, so all 4 steps I have written in this diagram, so you can see. But according to the recursive nature, if this instruction is executing and we are calling this function first time for left part, so this is a recursive call. This is again recursive function ms. So this will complete first, and then when we can move to the second instruction. If the first instruction is not completed yet, then we cannot move. So this is again recursive call. Once again we have 4 step. Okay, because here n equal to 2, size is equal to 2. This is not a base case. Okay, so once again we will write this l equal to ms. Now this time left is only 4. We have only list of size 4. Okay, and r equal to ms, and here right size is 1. Okay, and now sorted equal to m merge of l comma r and return. Okay, so this is return statement s. Okay, now this will execute first completely. Okay, so now we have moved here. Once again you can see this is the recursive call again ms, but this time n equal to 1. Okay, and this is the base case here. This is the base case here, n is less than equal to 1. Okay, we are directly returning l. Okay, what l we have received right now, we will directly return this. So in this case, by this function will be replaced by list l, this 4. Correct? So what value you have received at this time in l? Only one list 4. Okay, now so this instruction is executed completely. This one list is assigned to this l. Now you will move to the this lower instruction r equal to ms1. So this once again this is a recursive call, but you have a list input size is 1. So this is directly return l. Okay, so return l means you will directly get this list 1 from here. Okay, now l equal to, you have received 4, this list, this is now complete. These two instructions is completed. Now you will perform this sorted call. Okay, so s sorted list equal to merge function l or r. Now this function is a separate function we have received, where we are getting 2 sorted lists. So one sorted list is 4 and another list is 1, and we are combining these two lists and we are getting one sorted list. So 1 comma 4 like this. Okay, and that list we are assigning to s. Okay, so that means this merge function will replaced by this 1 comma 4. Okay, and after that we are returning this s to the our previous call where we are coming from. So that means 1 comma 4 will be replaced by this part. So this part will be replaced by 1 comma 4. Okay, now l equal to this list is assigned. Now this part is completed, then you will move to the second part, second instruction for this level. and this is again recursive part. Here you have two elements. Now once, so this part is overall completed, then that means this first instruction is completed here at this level. Now you will move to the second instruction of this level, r equal to ms 3 by 2. Then once again 4 steps. Okay, so l equal to ms, sorry, l equal to ms only 3. Okay, r equal to ms 2, and s equal to merge l comma r. Okay, and return s. Okay, this is the fourth steps. Okay, so in this process same things. So this is only single element we have in this recursive call. We will directly return one list 3. Okay, now this first instruction is completed, you will move to the second instruction to execute. So r equal to ms2, so this 2 will be assigned, this list will be assigned to r. So now you have l equal to 3 in the list, r equal to 2 in the list, and you will pass this list l or r to the merge function, and you will get sorted merge. Okay, so this is 2 comma 3, one list. Okay, this will be assigned to s here, and this s will be returned to the main call, and this will be replaced by this 2 comma 3. Okay, now you have l here and r here. Now next instruction is sorted, and then merge these two sorted. So this 1 comma 4 and 2 comma 3. Okay, so this 2 comma 3 is now two sorted list. Then you will get one merges list. So after combining this both, and this will, so this function will, merge function will be replaced by one sorted list. So this is 1 comma 2 comma 3 comma 4. Okay, here from this, and return s. So this list will be returned to this main function, and this function, this will be returned by this list 1 comma 2 comma 3 comma 4, and this is the sorted list. So in this way, this recursive call is actually executing. Is this clear?
Clear. Thank you very much.
Yes,
Thank
sir.
you. Thank you.
Okay, so just remember this. So merge sort complexity in all cases is n log n. Okay, not dependent on the input order. So if you pass any type of order, you will get the n log n complexity. Yeah, so recurrence relation, I just want to explain that. So we have recurrence relation for Tn equal to 2Tn by 2 n plus n. Okay, so this is for merge function, and this is the recursive call. 2 times we are calling the same function again. So we can understand this by the recurrence tree method. That method is not too much difficult. We can I am just explaining this. So initially we have Tn size. Okay, now this is the first problem. After that, this is the sub problems we have, and 2 times we are calling this problem. So we can draw this like, okay, Tn by 2 and Tn by 2. Okay, like this. So these are the two separate problems we are calling recursively. And if we are calling first problem, so this is taking out of n time for merging. So this is n time we can write merging. If we are giving n input, merging operation is taking n time. So now the recursive call, if we are passing n by 2 input, so that will take n by 2 steps for merging. So this is separate problem. Okay, and similarly, if you are passing n by 2 for the second problem, this will also take n by 2 steps for merging. Okay, so at this level, if you add both n by 2 plus n by 2, you will get total n. Okay, once again, this will recursively call again. So T n by 4. Okay, and T n by 4. Correct, we are dividing again this part. Similarly, we will divide again T n by 4 and T n by 4. Okay, so if we are passing n by 4 input, definitely merge will take n by 4. Same, plus n by 4 plus n by 4 plus n by 4. Okay, so if you add all the merge operations at this level, you will total is n again. And you can see every time we are dividing the input size by 2. So that size is dividing like this, n by 2, then n by 4, each level. Okay, so this is the one level, this is the second, this is third level, n by 8 in this manner. So this is the divide operation. So that means total log n steps is required to reach at the base case 1. Okay, so total log n levels are required, and each level is taking order of n time. Okay, so we have total log n level. So log n, each level have n times, so we can write like n log n total time is required. Okay, so this is the overall complexity for the merge sort.
The log is because we are bisecting.
We are dividing, so this problem by half every time. So you can see that we will just reach at the base case in log n steps by dividing.
And
So
sir,
each level we are getting the same amount of time.
and sir, how we get n? Getting it?
Sorry, how?
So how we get n?
So this is because of this merge operation, na? So initially merge
No, n log n, in n log n we are getting n.
n is for this merge operation. Each level, if you have input n, then merge operation is taking merge operation is performing merging operation between n by 2 plus n by 2 and returning the list of size n. So that will compare each element one by one. It will take order of n operation. Okay, so merge operation complexity is order of n.
So it will be in plus n. There will be plus n.
So plus n we have written. So I am just representing this Tn. So at this level, when we have input size n, so overall merge operation is taking n time, n steps.
Yes.
Now this problem is divided into two recursive calls, two separate problems. Okay, so these two separate problems we have now at this level. So each separate problem, now input you have just passes half.
Yes.
So same thing. So merge operation will also take half time.
Yes, sir.
Okay, similar, the second recursive call, that is also a separate problem. If you are passing half input, that will also take half size amount of time for the merging. Okay, initially if you are passing n equal to 100 here, so it is taking 100 steps for merging. Now you are passing 50 input here, so it will take 50 and it will take 50 plus 50 100 equal to n. Okay,
so the total time complexity will be the n log n plus n, right?
no, why n? Here at
So
here at each level we are calculating the overall time. So this is n by 2 and n by 2 overall is n.
Sir,
At this level I am just counting.
sir, so it will be in plus, no, sir, log n plus n.
No, why?
Overall, sir, overall, not for this level, overall.
Overall we will calculate this. So first thing, level wise is clear.
Yes, sir,
because,
level wise clear.
Because we are receiving n by 2 size sorted list here, and then we are merging this. Okay, so we are getting merge operation of n by 2 here. Okay, in this manner, each level you are getting n operation. Correct?
Yes, sir.
How many levels we have?
N.
Log n.
Log n, no? So each level you have n operation and you have log n levels. So simple n into log n.
Yes.
Okay. So this is simple multiplication. So in this manner, so we will also learn the this recursion tree in the B-kit, where we will also check. So here we are getting the same amount of time at each level. So we are directly figuring out that number of level into amount of each level. But sometimes this amount of this operation is actually sometimes increase, sometimes decrease. So at that time, what we can do, so we will use that some formula which is defined by the recursion tree. So that we will discuss. Okay, at the B-kit. But for some basic problems, so similarly for binary search problems. So in binary search problems, because what is the recurrence relation for binary search problem? So we have Tn initial problem, and in that problem we are calling the same algorithms on the half part every time. Okay, so that means we are calling recursively. If we are implementing binary search by recursive function, so then we will use this recurrence relation. Okay, and we will pass half size. Now we are calling our recursive function only one time in each steps. And apart from that, we are performing some constant operation, comparison operation. So that is constant one. So this is the recurrence relation for binary search. Okay, so in this manner, so if you draw the recurrence tree for this, so there's no recurrence tree. This is simply steps. So one constant time. Okay, next call T n by 2, but still constant time is fixed 1. Correct? So this constant is not dependent on the input size. So this will remain 1. So T n by 4 like this. one step. So in that manner, you will reach at the one base case. So total levels are required log n. Okay, and what amount of work we are using at each level? One. So one into log n. So log n overall. Okay, but we will also just look the recursion tree for quick sort in the next week, so that we will also repeat. So yeah, this is the merge sort, and also just remember this basic operation of the Python, how much time actually it takes internally. So if you are performing in operation in the Python, okay, so that in operation, suppose um, you have a one list L. Sometimes you perform to for searching if element is in L or not. Okay, so if like 5 in L, this is the simple one line operation if condition, but this is not a constant operation. Okay, this in is actually defined in this manner. So internally, this operation is performed because you cannot find out the element in the list without comparing the elements. But in Python, you can perform this operation by writing only this syntax. But internally, definitely comparison is required if you are searching something. If your list is not sorted, then definitely some comparison is required to find out that. So this operation is written in one line, but internally it takes order of n, because without comparison it is not possible that you can return the elements directly in the list from the list. So this operation takes order of n times. So just slicing takes n times. So I have just mentioned this some basic operation which we used in the list or different data structures. So just read this and to get some idea of how much operation it takes times. Okay, so
Amortized means absolute, right? Amortized worst case, absolute worst case.
yes, so amortize is just a different way of the calculation. So where if you find out the some very rare situation, if you are finding out some maximum time, so at that time the calculation way is different actually. So suppose most of the time you are getting the solution log n, okay, or log n or less than, but in some rare case, one or two time situation, you are getting more than log n times. So
So
that
the extreme worst case possible to exist.
but that actually time we ignored that, actually we not consider as a overall complexity, but because that is the rare situation. So if we combine the overall time, so we can consider as a log n time as a overall worst case situations. So rare situation sometimes we ignored actually. So that is the different way of the amortized. So like this dictionary things, okay, so dictionary things we consider as a searching time is uh, constant. Okay, in dictionary searching time is a constant because we know the we can directly calculate the index of the any element by the some formula. Okay, so we can directly calculate the index by the value and we can directly return the value. Okay, so this is a constant time. But what happened, some confliction is there, that conflict is there, one problem is there with the dictionary. So if your memory is full in some way, or if your memory is full, then you are performing the dictionary operation and you are not finding any empty space in your memory. So at that time, that confliction, that operation will be repeat multiple times. So that is the rare situation when your computer system memory will be become full. So that type of situation, that operation will take more time, but that rare situation we can ignore. So then we can calculate the complexity in different way. Okay, so we will discuss these things in the later. So I hope already 4 hours is done.
Sir, last question, sir. In lecture 2.3, sir, you can open the portal.
Lecture 2.3.
So, near 8 minutes, sir has discussed one question. Number of bits function. Sir, sir was saying that we have to assume n as the number of digits. It is right or wrong?
That is, okay, 1 second. Number of bits is binary representation of n. Log n steps for n to reach 1. Okay. For a number theoretically problems, input size is number of digit. Linear in the input size. Okay. So what we are asking that if one input is given, okay, n is given,
Yes.
how you can calculate the binary number for that, and how many digits are required in the binary number? Okay, suppose if any decimal value is given like 10.
Yes.
Okay, this is value is given n for n equal to 10. So if we just find out that how many digits are required of the binary equivalent of this, so how you
Yes.
can calculate you can apply the division method.
Yes.
So 10 just divide by so that divide by 2. Okay, so what reminder you are getting at every steps, so you can write here. So what reminder you will get? 0 5. Okay, so just write that quotient part here. Once again repeat this process. So what reminder you will get? 1 2. Okay, 2 into 2 4, which is less. Now once again repeat this process, so 0 reminder you will get 1. Okay, and once again 0, and this is 1. Okay, now you are getting this value, and just read this like this. Okay, so 1 0 1 0, so this is equivalent to 10 value in the decimal. This is a binary.
Yes, sir.
So now how many times you are dividing this?
So 4 times.
4 times, no?
Yes,
So every time you are dividing by 2, so this is log n steps.
Yes, sir.
Okay,
Yes, sir.
so that is also representing the total number of digit in the binary. So 4 times 4 bits is required.
Sir,
So,
means we are not taking n as digits of the number input number.
so here if you are representing this log n complexity, but this n is actually, this is n is equal to this value.
Yes, sir. That I am saying, sir. But in lecture, sir was saying that it was digit of n.
But this is also equivalent to digit, na? So log n is also equivalent to digit, number of digit.
Number of digit of means in binary number, na?
Binary number.
But not in decimal number.
No, not decimal. Here we are just figuring out the number of digit in binary number.
Okay.
Okay, not in the decimal number.
Okay.
Because
Sir.
of that, we are so you can see in the red line number of bits in the binary representation of n.
Okay, sir. Got it.
Okay, so this log n is directly related to the number of digit in binary here.
Okay, sir. Thank you, sir.
Okay. Okay, so I hope so today's 4 hour. Okay, any query? Has anyone?
No, sir.
Okay.
Thank you.
Thank you very much. Thank you. Good night.
Thanks. Good
We
night.
have the class day after tomorrow, right?
Yeah, on Friday. Otherwise, TS session is also there tomorrow at 5 to 7.
5 to 7 is not really possible.
But live coding session is on Friday.
Yeah, okay. TA session also will be recorded?
No, that session will not be recorded.
Too bad. Okay. All right. Thank you.
Okay, then.
Thank you, sir.
Thanks. Good night.